Good morning, everybody. Welcome back. We're going to start the third phase of our lecture series in fuel fundamentals. Thank you all for the interactions over the last couple of days. I think today you're in for a treat in fuel fundamentals with Professor Aamir Farooq in the morning and Professor Angela Violi in the afternoon. I know Professor Aamir has some exciting lectures and interactions planned, but I'll leave the surprises for him to disclose. So our first instructor for this Fuel Fundamentals lecture series is Professor Aamir Farooq. Professor Aamir got his PhD from Stanford, mechanical engineering in the group of Ron Hansen studying shock tubes and laser diagnostics. He was one of the earliest faculty members recruited here at KAUST in the Clean Combustion Research Center, and now currently our most longest standing faculty. He came in 2010, soon after the university opened, and of course was instrumental in hiring many of us afterwards. And he started a new lab, a lab in chemical kinetics and laser diagnostics. And within the last 7, 8 years or so, this lab has become really one of the best in the world for studying experimental kinetics, as well as developing new types of laser sensors for various types of applications. So he has a broad range of expertise in studying very elementary aspects of chemical kinetics using experimental methods, but then also developing laser diagnostics to probe kinetics, and then translating those sensor technologies to other real-world applications like biomedical sensors as well as environmental sensors. So we're very fortunate to have Professor Aamir present to all of you. I hope you take the opportunity to engage with him and learn a lot of his expertise in fuel fundamentals.
Okay. Thanks so much, Manny, for a very kind introduction. Good morning, everyone. I didn't hear back anything. Good morning, right? I need to see some excitation, yeah? some excitement, right? So we need to, it's early morning, so we should be all fresh. It's my pleasure to be talking to you guys, and again, I thank the organizing committee, Manny and Professor Bob Dibble for giving me the opportunity. Okay, so today we are going to talk about fuels. In the last couple of days, you have heard a lot about flames, their basics, their fundamentals, experiments, then engines, turbines, and so forth. But the key and the common aspect in all of them is the fuel, right? If there's no fuel, you can't run an engine, right? So fuel is the most fundamental aspect of all of the stories that we've been hearing. So we have we have 2 sessions today. So in the morning, I will be talking about fuel characterization, chemical kinetics experiments, and then if time allows, a little bit on diagnostics. And then in the afternoon, Professor Angela Violi, she will talk about surrogates for fuels and a bit on kinetic modeling, but then she will focus a lot on how aromatics and nanoparticles and so are formed. Okay, so with that, I'll begin first of all by acknowledging people. So these are my group members. Some of the work that I will present today is efforts of their hard work. So this is led by my research scientist, Dr. Binod Giri. Khalil manages everything in the lab. I have 2 really good postdocs, and then really bright PhD students who have really helped take our group and our research to where we are today. In addition, I would like to acknowledge these people whose slides either I borrowed, I've asked them, or they have kindly contributed to that. So Manny, Henry, Alicia Renzi, and Bill Green, as well as some of the PhD students from the center have been really helpful in providing me some information. And in my group, specifically, Fatih has helped quite a bit, along with Abad and Essen on preparing some of the slides that I have. Okay, so the first, I want to begin with a couple of quick questions, okay? Should it be a one-way instruction? What I mean by that is I don't consider this, although I'm standing really high up and you guys are there, but I wanted this to be more of like a class, right? So those of you who have taken classes with me, I really encourage interaction during the classes, right? So I don't want this to be a one-way instruction, and if that means that I can only cover a quarter of what I've planned, that's totally fine, right? So please ask lots of questions, okay? And if sending this ball around takes long, just shout out, okay? And I don't promise I have answers to all your questions because I'm presenting work from a lot of the members of the center, but those experts are here, right? So I'll be diverting the questions over to them, okay? So please feel free to ask questions at any point in time. Now that I've said that it's a course and not a presentation, then have you ever had a course without exams? Right? I mean, I haven't had one. So obviously, everyone says learning is the key, but knowing that there will be an exam really kind of keeps us focused, okay? So be ready for that then. There will be 2 quizzes into this class, okay? So it's a class, right? So take notes or pay attention to whatever we are doing. But then what will be the result? What's usually the result in a class? You get a grade, A, B, C, D, or in some classes you get a pass or fail, right? Should we do that? Give everyone, whether you understood fuel fundamentals or not, pass or fail? Maybe, but okay, let's keep it a little bit light. Instead, there will be prizes to be won, okay, based on the quiz. And not to tell you that I'm bluffing on everything, the prizes are here, okay, at the front. So based on your performance in the quiz, you will be, you have the opportunity to win prizes. Now, it could be just a pen, but it may as well be an iPad or something, right? So I don't know actually what's in those boxes. I mean, maybe I know, but. Okay, all right, so let's get started. So this is the plan for today. I will begin with some introduction, characterization, experiments, and diagnostics, okay? Now, on the introduction, actually, Tony Dean did an amazing job yesterday on telling you the landscape, where we stand in terms of our energy. And the thing here is that we just require energy for everything. Last month, we had a couple of really good talks, speakers coming from UT Austin and our own Ted Patsik, telling us about the energy scenario, some optimistic views, some pessimistic views, right? But the crux of all of that is we just require energy for everything, right? This entire hall, this lighting, my clothes, I mean, just everything depends on energy. And so just to put it in perspective, the world power consumption is about 16 terawatt, okay? Tera is what? Anyone speak out loud. 10 raised to power what? 12, okay? 10 raised to 12. So it's a really, really huge number, okay? And to put it in like maybe common sense, it's equivalent to having 20 into 100-watt light bulbs on for every human being, okay? That's how much energy we are consuming. And then you can look at the table on the right, and then it's basically the big suspects are China, US, and then Saudi Arabia is also not too far down there. Okay, and then Tony really discussed in detail these charts, so I will not spend any more time. But the point here is that even going to 2040, 2050, beyond this as well, the non-OECD or developing countries are going to need a lot more energy, and most of it would still come from oil, coal, and gas, with some contribution from renewables. Now, when you talk about renewables, yes, we see a lot of potential in solar and wind and so forth, but in transportation is actually a lot more tricky because there, the liquid-based fuels are going to remain dominant for a long period of time. Even currently, 90% of our transportation energy comes from liquid-based or oil, okay? And we have like 1.1 billion passenger cars currently, which is expected to increase to like 1.8 billion in the next couple of decades or so. So this scenario is going to remain like that. So in that context, and this is a point that many speakers have made before, but I just want to re-emphasize that if that's the scenario, then as combustion engineers and scientists, we need to optimize fuels and engines to achieve highest efficiency, lowest emissions. Again, Tony talked a lot about emissions, but I want to point out the last point, lowest well-to-wheel greenhouse gas emissions. Okay? That's the picture that we need to look at, especially when we compare our technologies against other technologies like electric cars and so forth. So then, in the fuel and engine optimization, I want to highlight 2 efforts that have been going on. So we have a large program with Saudi Aramco called FuelCom, and the idea here is to work on, so the pointer doesn't work on the screen. The idea is to work on new engine concepts along with fuels to get the maximum possible impact that we can have. A few years later, a program has been started in the US as well called CoOptima, where they're working on along the same lines as we've been doing here for some years. So these are the kind of efforts which are needed at a very rapid scale for us to make a big impact as combustion scientists. Okay, so fuel. As I said, fuel is the most important thing. So the first question is, what is a fuel? Anyone? Definition? Yes. Multi-component liquid, okay? Does it have to be a liquid? Okay. Could be solid, could be gas, right? Could have many forms. But what do we really want to get out of a fuel? So energy, excellent, right? So that's the main point. So fuel is a material that carries energy in chemical form, okay? Then what do we do with that chemical energy? So in most of the times when the fuel reacts, you convert that chemical energy to heat, okay? Most of the times, but not always. For example, in fuel cells or so forth, you can actually directly convert it to electric power as well, okay? Now, so I said there that in most cases, energy is released via chemical reactions, right? So chemical reactions happen. So that then tells me that I need to really understand those chemical reactions because that's the key there, okay? And each fuel, based on its chemical structure, would undergo different kind of chemical reactions. So those details are very important. Now, one point which is important to emphasize here is that the energy density of liquid fuels is way, way higher than anything else, okay? And that's really, really important for transportation. So I make that point by showing you first this energy density plot for batteries and how they have evolved over the years, right? So starting from 1985 to 2020, the Model 3 Tesla car, which is like behind by 2 years in its production. But anyways, so their energy density has increased a lot, but when you put it in perspective compared to gasoline and diesel, it's just minuscule even right now, right? So that's the challenge that the batteries or electric cars are facing. And yes, there should be effort in those, but we cannot deny the advantages which are provided to us by gasoline and diesel fuels, okay? Okay, so then the next question is that what properties do we really want in a fuel? So one, we want to just carry maybe the fuel and not the oxidizer, okay? That would be convenient. So we can take the second one from the atmosphere, which is air, okay? And primarily in air, there are a number of components there, but what really reacts is the oxygen, okay? Then we want to have high exothermicity so that the fuel releases a lot of heat, okay? And that's what's going to give us eventually work, okay? And then it should be available abundantly in nature. We need millions of tons, as I put on a slide before. And that's the challenge which is faced by what? The biofuels, right? Biofuels, a lot has been talked about, but most technologies that you have for biofuels, they just cannot match the volumes that you really need, okay? So that's why their impact so far is pretty small, okay? Then we want the fuel to be environmentally benign, okay? We want its exhaust to also be not affect our environment, okay? And then it's better if the both fuel and the exhaust are in gas or liquid. It becomes a messy to deal with solids, okay? So if you look at the entire space that's available to you, right, in the form of all the elements that we have, right, and you put just some basic criteria, it becomes very obvious that carbon and hydrogen have just a unique place, right? You can take any others and look at what happens to them if I use them as fuel. If I oxidize them, in some cases I'll make solid oxide, in some cases I'll make toxic elements, right? Some will not even give me enough enthalpy of oxidation, right? So if you just set a few simple criteria, you will come to the conclusion that hydrogen and carbon in this entire landscape of the periodic table are what really, and that's why the Mother Nature provided us with these, and we've been using that for useful purposes. You may be able to add some oxygen to it, as it is in biofuels, but then oxygen usually reduces the energy density. And in some cases, you can have nitrogen in there. Okay, so the fuels come in a variety of forms, right? So I've just listed some here. You can have gases, naphtha, gasoline, diesel, some solid fuels, and so forth, okay? So they come in a lot of different flavors, okay? So now, if you want to optimize the fuel engine, which I talked about earlier, then you need to do a multi-physics sort of understanding and operation and optimization, okay? And among those are fluid dynamics, thermodynamics, and reaction kinetics, okay? So this nice slide put together by Manny, which talks about that if you want to optimize the efficiency, power, and emission, those could be your really end goals, right? So then you need to understand the fuel, how temperature, pressure, and other parameters are affecting it. But the key here is that you have the three main pillars there of fluid, thermo, and reaction kinetics. And in today's talk, I will just focus on the last aspect of this entire puzzle. So how do we do the fuel optimization process in our center? So we begin with a very complex fuel, and we want to understand its molecular level characterization. Then we want to have a simpler representation. A surrogate is what? It's just a simpler representation of the fuel that we are going to use, okay? Then we build some models for those surrogates. We perform experiments, and there's actually a feedback loop. It doesn't always happen like this. Sometimes you do perform experiments first and then build the models. But there's a feedback that goes on there. And once you have that, then based on that, you can predict the performance of a device, of an energy device, and see also how you can optimize it in the best possible fashion. And then you can go ahead and run engines and optimization. And again, sometimes it doesn't exactly happen in the same sequence, but these are the key steps which you would like to have. Okay. So now in this entire sort of puzzle or picture, what I'm going to talk about in today's lecture, or in today's class, I should say, is the most characterization, and then on the experimental part of it. Okay, I'll touch a little bit on the other aspects, but those are going to be the two key aspects. Okay, any questions so far? Oh, okay, so that was just introduction. So hopefully, and again, you guys asked a lot of questions yesterday to Tony Dean about that, and I think that was really, really good. Okay, okay, so let's begin with fuel characterization. Okay, so I've listed here a few topics that I will go through in the next 15-20 minutes or so. So in a fuel, what you care about are its chemical properties, okay, and you also care about its physical properties. Okay, so we'll see how you determine the chemical nature of the fuel and how you determine some of the physical properties of the fuel. Okay, but why? Why do we need to do that? The reason we need to do that is because the fuels, the real fuels that we have, gasoline, diesel, jet fuels, and so forth, they are a really complex mixture of a lot of hydrocarbons. Okay, so you can have anywhere from C4 to C20 if it's a really, really heavy distillate fuel. Okay, so this shows the different carbon number peaks that you have and how you discover, how you get them as a function of temperature. Okay, if you look at something like a kerosene fuel, okay, it has different kind of classes of compounds, alkyl benzenes, isoalkanes. It tends to have quite a bit of cycloalkanes. Okay, so you begin with, obviously, when you take a crude oil out of the ground, you begin with this sort of black column. But what it eventually has, and what you recover from a distillation process, is really a spectrum, a continuum, right? A continuum of a lot of components varying in their boiling point, varying in their properties, varying in their structure. Okay, so you can have really light components like ethane and so forth, methane, obviously, if the gas is there, and then you can go to really, really heavy stuff like vacuum residual oil and so forth. So, and you make some cuts into this distillation process to get a specific fuel. Okay, but that fuel is going to still have some continuum or a lot of subparts in it. Okay, so the fuel is complex. That's the point, right? So if we look, for example, the boiling point range of a different fuels, right? So at the low end, so we have the boiling point on this x-axis here, and the carbon numbers on the right. So at the low end, you have LPG, naphthas, then you go to gasoline. Then as you become heavier and heavier, you go to diesel and lube oil and HFO and so forth. So, but what you see, the important point to see here is that there is a range, right? Because there are many components in there, so it's not just one point or one carbon number or one boiling point. Okay. Even if you look at gasolines at different times of the year, if you look at different geographical locations, it is going to have different composition and different properties. Okay, so the chart on the right shows that how the distillation will be different between a summer or a winter gasoline. Okay, so the conclusion from this, just a couple of slides, is that the real fuels are complex mixtures of hundreds to thousands of components in some cases. Okay, so before we can begin any discussion on the fuel and see what we can do with it, right, we need to determine what properties do we want in this fuel, what are really going to affect the engine performance or any other energy device, how we can characterize that fuel, okay, and that's what I will focus on, and then propose a simpler representation or surrogate for that fuel. Now, in terms of what properties are important, so Bent Johansson gave you a really excellent lecture on talking about different kind of engines that we have, okay? The diesel engine, gasoline, HCCI, or advanced engines. What is important to understand for the context of this talk is that the fuel properties which affect the energy conversion or combustion in these engines could be different as you go from one engine to another engine, okay? So for example, if you talk about a diesel engine where you spray your fuel into hot gases, right? In that case, the chemical parameter which becomes important is the cetane number of the fuel, which is how we describe diesel fuels. And I'll talk about that in a bit, okay? because it's an injection process of a liquid, which goes and then evaporates, physical properties become very important, right? How does the evaporation take place? And in terms of ignition, it's mostly hot ignition or high temperature chemistry, which affects the chemical processes. If you talk about a spark ignition process, then because you are advancing a flame through the mixture, through the spark, then it tends to be the flame moves at a specific speed, a slow ignition, and then you describe the fuel by research octane number or motor octane number, okay? In order to describe what happens in the end gas, you need to understand the knocking, and that's again a very chemical kinetic-based phenomena, okay? And now maybe along with higher temperature chemistry, intermediate temperature chemistry becomes important, okay? And physical properties are still important in finding out what will be the temperature and pressure as you compress this fuel-air mixture, okay? Now, when you go to these advanced engines that Ben described in detail, like HCCI or any low-temperature version of those, then again, the chemical kinetics actually becomes even way, way more important, because that could be your only control criteria, unless you have some control loop that, again, Professor Johansson described. In these cases, maybe now the low-temperature chemistry also becomes important, okay, along with intermediate and high-temperature chemistry. And again, physical properties would still remain important. So the key point here is that based on the device that we have or the operation that we have, there will be different properties which we need to worry about, okay? So now how do we determine these properties? So one of the very fundamental tool that we use is called a DHA, or process, detailed hydrocarbon analysis, okay? So that helps you really know the structure or the chemical nature of this really complex mixture that you have, okay? Primarily, it is used for analyzing gasoline fuels. It could be done for diesel, but it becomes a lot more tricky to do that. So what you get eventually from this analysis is that you want to know how many paraffins are there, how many isoparaffins are there, olefins, and so forth in the entire fuel that you have. Okay, and there's a specific ASTM standard that is used to carry out these analyses. Okay, so you bring in your fuel into this typical GCMS. Okay, and then it goes through the column. There's a retention time. Actually, many times multiple columns are used to get high resolution or separate out the components. What becomes very important is to be able to separate out chemical compounds which may be appearing in this time or retention time diagram, right? So for example, you need to really separate out the peaks of, as it says there, toluene and 2,3,3-trimethylpentane, which have very different chemical structure, right? But they're appearing close there, so you need to be able to separate that out. So how does the typical data looks like from DHA? Once you have performed it according to the method, you get a listing of your compounds, different classes, what is their weight percent, volume percent, and what is their mole percent. Okay, so that's all now very, very important information that we can use to understand the fuel. Okay, you can then group that into different kinds. You can look at what are the carbon numbers. So this analysis was done for a typical gasoline fuel. Okay, so in that case, you see that it's kind of centered around C7, C8. Okay, you see the C7, C8 has higher mole percentage. Okay, and then you can also group into a specific class there and see how many carbon numbers are there in each of those classes. Okay, so this is now the entire story or entire chemical description of the fuel from a structural perspective. Okay, now once you have that, you can use that to calculate, or I should say estimate, a lot of properties of the fuel, right? So like you can get the molecular weight, these octane numbers, okay, HC ratio, density, physical properties, and so forth, okay? So as an example, it shows here the average molecular weight for this gasoline fuel was around 90, okay? And then some other physical properties. But these are estimated, okay? So based on some blending rules, for example. So it sometimes becomes important for you to go on and actually determine these properties, and that's what I'll talk about next. Okay, this DHA will give me an octane number, but it may not be very accurate. So I may have to go on and perform additional experiments to measure the octane number or measure the density or molecular weight of the fuel. Okay, because it uses some rules which may not be very accurate. So one of the tools now, by the way, just so that you stay. You kind of know the order. So on the right at the top, you will be seeing the topics that we are covering, okay? So now we have moved on in chemical properties to the second topic, ignition quality tester, okay? And we are still on the second topic of fuel characterization. Okay, so the IQT, this is a picture of the IQT that we have here in our center, and you would have seen it during your lab visit. Okay, it's a very nice tool for quickly screening the fuels. Okay, if you want to really quickly know the ignition properties of a fuel, you need a very small amount of fuel, and you can perform this experiment very quickly. Okay, and there's again an ASTM standard used for that. It's primarily used to measure the C10 number of the fuel. Okay, so on the right you see a schematic. So what happens there is that you inject the fuel, okay, and then there are some pressure sensors there, and after it evaporates, it is injected into a hot environment. So air is already there at the desired high temperature and pressure, okay, and then it evaporates and it undergoes auto ignition, and so then with the pressure sensor you can determine when that has happened, okay. So this is on the left is a simulation performed in Professor Hongim's group on the evaporation. So fuel was injected from there. So it's the spray process, then it's evaporating, some along the walls, and then you see the ignition happening all along. Okay, and so that is then shown on the right-hand side on this time versus pressure picture, for example. Okay, and so from there, when you see this really large spike in pressure, that's what your ignition delay time is. Okay? But what is important to emphasize here for this device, as you again see in the simulation, is that there are two processes which are happening here, sort of sometimes in sync and sometimes overlapping, which is that first, the physical processes are important. The fuel evaporates, okay? And then after that, it undergoes ignition, okay? So it's a combined effect of both physical and chemical properties of the fuel, okay? So then you can look at a number of different fuels, real fuels and surrogates. It's a nice tool, again, to screen some surrogates. You can propose a surrogate and then compare it against the real fuel. There's just a lot of information in that chart, but what we are plotting is ignition delay time as a function of temperature. And I'll discuss that in detail later when I go to the shock tube. But the point here is that with the IQT, you can compare different fuels. You can compare their surrogates as well quite easily, okay? And what you eventually want to get the C10 number of the fuel, okay, which you can also get from a C10 CFR engine, for which there's a different ASTM method, but you can get it from the IQT by using these relationships. So once you have measured the ignition delay time at a specific temperature and pressure condition, you can then convert that to the C10 number of the fuel, okay, and then again use that to compare various fuels. Okay. We can, so this is the work done here in KAUST by PhD student Nimal Nasser. He has shown that there is also a correlation between the research octane number and the C10 number of the fuel, okay? So you see it there, the RON and the DCN are plotted. And in some cases, it works quite well. In some cases, we see some discrepancy from what the actual RON should be, as it's shown on the right-hand side, and what has been predicted from this correlation, okay? So there's this trying to use the IQT maybe sometimes out of its sweet spot, but it still gives valuable information. Okay, another technique that we use that has been used widely only recently for characterizing the fuels started from some work at Princeton, and now here at KAUST and Manny's group, a lot of work has been done on using NMR. So on the right, at the top is the picture of the NMR facility in KAUST. We have the world's best NMR characterization tools there. I think we have like 9 NMR facilities. So what NMR is basically, what it does is that it looks at the magnetic properties of the atomic nuclei, okay? So a specific magnetic field is applied around a sample of the fuel. So you inject it in there, okay? And then you have obviously some detectors after that, okay, to look at how the fuel responds to the applied magnetic field, and that would depend upon the chemical nature of the nuclei, okay? So as an example, what I show on the bottom there is that if you had put ethanol in there, you would see some peaks there, okay, as a function of the chemical shift, and those depend upon where the H atom is, okay? So if the H atom is on the first methyl group, or the second CH2 group, or the last OH group, it would appear at a different place in the chemical shift, okay? And because there's only one H atom there, so you see that small the sharp peak in the middle for that H atom, okay? So that's how you can basically know the structure of a molecule by applying the NMR method, okay? Okay. So what has been used a lot to characterize the fuels is the 1H NMR spectra. Okay, so the 1H method can basically help you know what is the type of the hydrogen atoms which are there. Okay, contrast with that is the 13C method, which I'll talk about on the next slide. But this basically helps us quantify. Again, you look at the chemical shifts, which are shown there, and then from there, you can really understand the what chemical groups that you have in your fuel, okay? So each functional group then, for example, how many CH3 groups you have, how many CH2 groups you have, paraffinic or coming from olefinic groups, okay? And so that's how you can delve deeper into the exact structure of the fuel, okay? So this is a comparison here of what you can get from the 1H NMR spectra versus the 13C, okay? So again, it's based on the deuteration in that case, or isotopic substitution method, okay? The 13C method tends to be less sensitive than the 1H method, and the 13C method is used to look at where more the carbon positions, okay? So in this case, we are looking at the hydrogen positions in different places in the molecule, and there we are looking at the carbon positions, which again, based on what is the sort of the neighbor or the structure of the carbon around that, the chemical shift will vary as you go along. So we have used this method a lot, for example, to characterize diesel fuels, which tend to be very difficult to do with DHA. So additional use that we can make with this is we can compare surrogates and real fuels. So what we show on the right-hand side is a fuel and a surrogate, different kind of phase fuels that we used here. And these bars you see for paraffinic, olefinic, or other groups that help us really quantify and know whether the surrogate is working as we would like it to work. Okay. So before I actually talk about the CFR engine, any questions? I said it should be a class, but it seems like it's still a presentation. Yeah, okay.
So we saw the result from IQT for different fuels. So did you count for the automation? Because you are using the same spray with different fuels. So the comparison for the ignition delay will not be apple to apple.
Yeah. So as I said, that in an IQT, you have the injection process, right? Yeah. So then the fuel will evaporate, right? Yeah. And so that will definitely affect the overall ignition delay time, right? Yeah. And so that's why we say that the physical properties as well as the chemical properties matter in the total ignition delay time that you measure in an IQT, okay? Yeah. Having said that, if we look at a range of similar fuels, we still see a good correlation between, as I said, the RON and the ignition delay time that you measure there, right? So there is some correlation there, but definitely the physical properties affect the total ignition delay time.
Because I used FIT, and they have this problem when I use two different fuels.
Yeah.
So yeah.
Sure. No, that's a valid point. Yep.
Hi. So the NMR testing you do, when you run that, do you have to put in a known sample and get the result out? Or can you kind of probe an unknown molecule in that way?
You can do it with unknown, and that's the key, right? That's the idea, that you can put a fuel for which you know nothing about, right? And then by carrying out the NMR process, you can then know the different parts or different structures that are in there. Right?
Okay.
So maybe you want to add, Manny, anything to that?
What?
There's an internal standard together with the mixture.
Okay. And can you describe a little more the difference between the H and the C, the H1 and the C13?
Yeah.
Is there very basic, like, how does that work, the difference?
I mean, just one is looking at the hydrogen shift, the other one is looking at the carbon.
Okay. And it's the same piece of equipment, or?
Yeah, you can do it in the same machine.
Okay. Thanks.
Okay. Anyone else?
How bulky is this NMR device? Like, can you have it inside your vehicle? No.
It's the way it is right now. It's pretty big.
It's
right?
pretty big.
Yeah. Okay. Let's go on, and then I'll give you more chance. So hopefully you're taking notes. Some of this could be in the quiz. Okay. Okay, the CFR engine. The CFR engine is used to measure the RON and MON of the fuel. Okay, it's a very standard device that you have in refineries. Okay, the reference that we use is isooctane, has an octane number of 100, and N-heptane, which is given a reference value of octane number of 0. Okay, So both the tests, the RON and the MON tests, are run at different conditions. The RON test is run at 600 RPM with an inlet air temperature of 52, whereas the MON test is run at higher RPM and higher temperature. And that's also depicted later on as if I get the chance to talk about on how it affects the comparison with ignition delay time. So this is the MON test, in a sense, is a more severe testing of the fuel compared to the RON test. Okay? So this is a very standard device, and this is a picture of the engine that's in our center that you would have seen. It has been modified to do a lot more than what is done in the refineries. Okay, so you have your equivalence ratio sensor there, or lambda sensor, your compression ratio there, and then other parts are there. Okay. So what you see eventually from running a fuel in a CFR engine is that as a function of crank angle degrees, the pressure rises and depends upon the compression ratio, whether it happens earlier or sooner. So in those cases, the compression ratio is different, 16 or 14. And then eventually what you do is that you compare your unknown fuel to a mixture of N-heptane and isooctane. And that's shown on the right there. Okay. So you see at what compression ratio did your unknown fuel ignited, okay, and then you compare it with a PRF mixture of N-heptane and isooctane to assign it a RON or a MON number. Okay, okay, so I put this picture here just to not ask the question that what kind of fuel you will use in a Ferrari, right? Whether it will be 91 or 95, but I put this question to this picture there to ask you that those numbers on the right that you see are from a US pump, and these ones are from the left are from a Saudi pump, okay? So why are those numbers lower than these numbers? Anyone? Abad knows it.
It's a RON and MON.
Sorry?
The characterization is based on MON in the US and RON in here.
So this one you said is RON, yeah? And what about that one?
MON.
You're close, but not exactly. Abad, you want to shout it out?
Or it might be average.
Average. That's the answer, right? And actually, it says it there in fine print, right? You can read it. So in the US, they report both RON and MON, an average of that, which is also called the AKI, okay, R plus M by 2, whereas in Saudi Arabia, we use the RON numbers. And by the way, recently, you know that in Saudi Arabia, the price of fuel has increased, right? And so before, many people here and my friends, they were just going to the pump and putting 95 without even thinking whether their car really needs it or not. Now you find a lot of these websites coming up showing, find out whether your car really needs 95 or not, right? So now it makes a difference. And really, you need to know what your manufacturer has specified, right? Whether you actually need the higher octane requirement or not. Okay, so that was all on the chemical properties. Okay, so I talked about different ways to get chemical properties. Now, you may also want to know something about the physical properties of the fuel. Okay, so one of the very important physical property of the fuel is how it evaporates. Okay, or the distillation. Okay, so there's an ASTM standard for that. There's an ASTM standard for almost everything that you want to measure, and it's good to follow that. Okay. So it basically helps us know how a complex mixture of fuel evaporates. This is a standard picture that you would have seen in your basic chemical engineering, okay, on how fractional distillation happens. The picture on the right is a device that we can use in a lab, for example, and usually it's performed at ambient pressure conditions, okay? So here I show the distillation curve of a few fuels that we have tested here. So 4-phase fuels, and you see as a function of volume fraction of the fuel evaporated versus the temperature at which you are getting different fractions. Although these are all four are gasolines, right? But their chemical nature is different, which then affects the physical property or evaporation as well. So for example, the phase G and the phase J fuels have higher fractions of aromatics and other species which evaporate later or which evaporate at higher boiling points. Okay? So that's something we can do. Now, viscosity, this is maybe from standard physics book. Basically, there's also an ASTM standard for that. That's also very important for fuels, for us to know how viscous it may or may not be. So you make it flow through a capillary, basically, and then with a calibrated viscometer and measuring the time, the flow time, you can measure the viscosity of the fuel. Okay. Likewise, the density of the fuel or its specific gravity is also a very important feature that you would want to know. And the standard device that you use is a hydrometer, which compares how it behaves compared to water, basically. Okay? So you put your fuel in the outside container, you insert a a hydrometer with a specific temperature there. And once equilibrium has reached, you can read out how heavy or light this mixture is compared to that. So there's an ASTM standard again for that. Okay, so with that, again, I will take a little bit of pause because then we'll be moving to the next topic on chemical kinetics experiments. So what we all talked about so far was how to characterize the fuel, how to characterize it chemically, and how to characterize it physically, okay? Any questions? Yes. I can hear you, yeah. Nice throw.
Yeah, you've mentioned that you can measure the run and using the CFR and using the IQT. So what's the difference between if you get the result from CFR and IQT? Is there both are accurate or? So
the standard is to use the CFR engine, obviously, right? And the process is very different what happens in a CFR engine versus in an IQT, right? So IQT just gives you an ignition delay time. Okay, an ignition delay time. And that then you convert to a DCN, a cetane number, okay? And then what has been shown here, recently work, is that that can be correlated with RON, okay? And sometimes we see good agreement between the RON measured in a CFR engine, okay, and the RON that you have derived from this entire process of the IQT, okay? But sometimes you have also seen some deviations, okay? So what I would say, if you are saying what would you trust as a standard, that's the CFR, right? This is because that's what you should be normally used for measuring RON. Okay. But the reason you may prefer using an IQT is just faster, right? It's just more, you can do it much more quickly looking at different fuels than would be possible in a CFR engine.
Yeah, but there are some factors in the IQT that you don't count, like in the CFR. So, I mean, yeah.
Absolutely, yeah. So yeah, so again, it's just a very different way of measuring the reactivity of the fuel. But again, what has been shown is that there is a correlation that exists.
But is there any way to predict how accurate is this comparing to CFR?
I think the way is just looking at I know there is also some modeling work which has been done looking at that, but primarily you can look at the derived RON, which comes from the cetane number from the IQT, right? And then compare it to what you measure in a RON, right? And then again, this has been done here at KAUST in a couple of publications by Nimal, right? So he's just sitting right there, so he can tell you more about that.
I see. Okay.
Thank you.
During the fuel characterization, does the measurement of those properties depends on the pressure?
Yep, some of those properties could absolutely depend upon the pressure, right? For example, you can look at the distillation, right? So distillation we normally do at ambient pressure, right? At ambient conditions, but we know that the evaporation properties of a fuel depend upon the pressure, right? So that then likewise the IQT test, right? The IQT test could be done at different pressures. So, but absolutely that's a very, very good question, right? Depends upon, but like for example, when I talk about the DHA, right? When I talk about the NMR analysis, right? That's just telling us about the chemical nature or the functional groups that you have in there, right? So that's more generic and shouldn't depend upon how you perform the experiment.
Okay, thank you.
That's a very good point, though. Okay, so sounds like you have understood the entire fuel characterization. Okay, so ready for the quiz? Yeah?
Yes.
Okay. Where is my TA? Okay. All right, so it's yeah, just pass it along. And you have, okay, once it reaches you, you will have 90 seconds to do the quiz. Okay, not 90 seconds, 5 minutes. Okay, was it easy? No? Okay, then the next one is a little bit tougher, right? So hopefully you'll pay a little bit more attention, right? But I'll also give you more time for the next one. Okay, so we move on to the next part of the lecture, or not class, next part of the class, okay? But before actually I talk about that, I want to show you, there were some videos being played as you were doing the quiz, and it's okay, that was just to distract you. But now I want to show you another video, and It's not exactly related to what I'm going to talk, but I like it, right? So that's what I'm going to show you, okay? So this was, it's not, I don't like it because it's from Stanford where I was, but I like it because I think it's done really nicely. So it's going to show you a match, what happens when you light a match, okay? So a person is coming in, and he's doing the match as it is lighted on a match box, okay? And you're looking at Schlieren photography there at sort of high frame rates, okay? So you see those nice, really the structure of the exhaust that's coming from the tip of the match, okay? And then after a while, it's playing in slow motion. I'll actually let you watch and not say too much. The text on the right is also good. Okay, so far it was not actually lit in the sense that now the combustion products are going to come out.
The music's not as good.
Absolutely. Actually, I think, I don't know if there is, but it didn't, the music didn't work out. So now a person comes in and he tries to extinguish the match, okay? And usually we find that it's very easy to extinguish a match, right? You just do this, it happens. But in this case, he's probably not blowing it as hard, okay? So it's, but it affects that. And now you see that really amazing turbulent structure, right? That's formed, the turbulent eddies from blowing the air that comes there. And it's probably part of that is caused by the tip, which is there, okay? So the next quiz question could be, as a hint, is that what was the Reynolds number in that, and that blow that came in? The hint is 10,000 frames per second. Okay, so but what is also interesting is that because he probably didn't blow hard enough, it actually eventually reignites. Okay, so the match, they must have done a few experiments to see this. Okay, why do I show this video? Again, as I said, it's not exactly related, but I show this to tell you that even a simple match, right? We think of the match, it's really simple. Even that is so, I can stay on the acknowledgement, but okay, that happened, sorry. Even that is it's very complicated, right? So you see a lot of structures, initially laminar structure, obviously, right? And then once someone blows in, there's this turbulent structure there, there's fuel burning and so forth. Even a simple match is very complicated. So it's not a good idea, I mean, you can do this, but probably to shine up your lasers and try to understand the match as it is burning. You can do that, and you will also learn something, but what is important is actually to isolate the subjects, isolate the phenomena. Okay? And that's the focus of my next part of the presentation, is to isolate on chemical reactions, isolate the fuel processes, and really try to understand those in the absence of fluid mechanics or turbulence or heat transfer. Okay? So again, I put these questions, why, what, and how, again, so that we should be asking questions all the time. We want efficient engines. We've said it many times. But we need to understand the chemical kinetics of fuels, okay? And we want to do it in a way that we can decouple the chemical kinetics from fluid mechanics and other physics that goes on there, okay? So we want to look at the reaction rates, the chemical kinetic models, and how fuels burn, and we want to do this in some controlled environments, okay? So, so before I go on, I just want to point out from this nice slide is that what we want to really focus on is on the left part of this picture, the kinetics, okay, where transients are happening. So some chemical reaction is starting before you reach an equilibrium condition, which is where when thermodynamics takes over, okay? So at that point, everything is governed by the equilibrium or equilibrium constant and so forth. But this is the left side of this picture. The kinetics is what we want to focus on because that affects what a lot of transient processes that we are studying. For example, the pollutant formation, the knocking process, and so forth that we see in engines, okay? So I show the, over there, the very simple reaction, H2 plus half O2 going to H2O, which is, we call it's the overall oxidation reaction, or the global reaction, okay? But it comprises of, it's not how this happens. This is not how actually the hydrogen and oxygen come together to make water. It actually comprises of a number of individual reactions, okay? And so now this is the basis of understanding the chemical kinetics or building models, is that you need to get to the basic level, the elementary level. So that global reaction comprises a bunch of reactions, 19 in this specific model. Okay, you have some chain branching reactions, some propagation reactions, sometimes some termination reactions are there as well. And so all of those have to be put together to really describe how hydrogen and oxygen come together to make water. Okay. What you see next to these reactions are the three coefficients, the three Arrhenius coefficients. Okay, so these reactions proceed according to how Arrhenius told us that they exponentially depend upon temperature. And usually these come from some sort of fitting, and sometimes from theoretical analysis as well. Okay, so that's how you will be able to describe the hydrogen-oxygen oxidation. Okay. And if generically, and this is something that was talked on the first and second day a little bit, generically you can look at the oxidation of any fuel as comprised of some initiation, propagation, and termination reactions. Now the propagation reactions, it depends what is the value of alpha in the second reaction. What that means is that if I start with one radical R, how many radicals am I making? Okay, so it could if it's just 1-to-1, or if you make more radicals than you started with, then that will be the branching reaction. So that's what we saw. If I go back on the first reaction there, H plus O2. So I started with one radical H, but I ended up with O plus OH, two active radicals. So that's why it's a branching reaction. And that specific reaction tends to be the key reaction in high temperature oxidation chemistry responsible for the chain branching nature of the system. Okay. So you have these kinds, and then what you can do is that you can put all of that together. You can do what is called a steady state approximation, meaning you say at steady state the concentration of this radical remains almost not constant, but what steady state means is that its consumption and its production is balanced. Okay, so you combine all of that, so you can get to a concentration of that radical, and then you ask the question that what would make this radical really increase exponentially, because the radical is what's going to explode your system. So you set that equal to 0, the denominator of that radical concentration equation at the top, okay? And so from there you get a condition for alpha. Again, alpha was what? The alpha was telling me how many radicals I'm making, and that expression in the blue over there tells you that it depends upon the rate constants, K2 and K3 and K4 of the reactions which were comprising it. It depends on some other concentrations, but it has to be greater than that specific value for you to see an explosive nature in your system. Okay. So I mentioned that just as a starting point, because this will help us understand when I go to a bit more detail of the chemical kinetic processes. Okay. So the chart on the right is really nice, and it shows various reactors that we can use to study chemical kinetics experimentally, okay? And the arrow shows degree of mixing, okay? So you can start on the top is the shock tube, okay? It's a homogeneous mixture, so you pre-mix fuel and air, and everything happens in a nice homogeneous fashion, okay? You can do the same in a rapid compression machine, in a turbulent flow reactor, but as you go down, then you look at the flow reactors, premixed flames, diffusion flames, then those are non-homogeneous processes, and you could still use those to study chemical kinetics or chemistry of fuels, but you get more sort of pure information in some ways about the chemistry of the fuel if you do it in homogeneous reactors. And another example of a homogeneous reactor is a jet-stirred reactor or a perfectly stirred reactor. Okay? So that's important. And what we will do in the next in the next phase of the lecture is that I'm going to sort of walk you through those reactors. Okay, so we'll start with the shock tube. We'll look at some of the reactors and see what kind of information that I get from these reactors, and that helps me understand the chemical nature of the fuel or its chemical kinetics. Okay, so I begin with the shock tube. Okay, it's my favorite device, and I say it's an ideal reactor for kinetics. And we used to say it ideal for some time, but now I put the ideal in inverted commas, and I'll come back to that when it may or may not be ideal. But anyways, basically it provides us very nice 0D homogeneous conditions to study high temperature, high pressure oxidation or pyrolysis. We have the driver section and the driven section. They are usually separated by a diaphragm of different materials, as you were seeing in that video. And the low pressure section is where you put your fuel-air mixture, which you want to study in this device. So then you pressurize your driver section with an inert gas, such as helium. The diaphragm bursts at some point in time. The shock wave travels to the right, hits, there's a wall there, end wall, and then it reflects back, okay? So that region, in the reflected shock wave region, or the red region, is where you try to make your measurements of the fuel oxidation, okay? So that's shown there also over there. So you start with the low pressure P1, with your beginning pressure. The first shock wave makes it P2, and then finally the second shock wave raises the pressure to the P5, or behind the reflected shock wave. And then you get some limited test time, and I'll talk about that on the next slide, what does that test time means. But in that test time is when you observe reactions or ignition of the fuel. So this is here we schematically show what kind of waves are generated in this shock tube. So you have a shock wave which is traveling to the right. You have some expansion waves which travel to the left. And then the shock wave hits the end wall, reflects back, and then there is usually some interaction after some time, either with the contact surface, which is the separation between driver and driven gas, or an interaction with the refraction wave or the expansion wave, which is coming from the other side. And that basically ends your experiment. Okay? Ends the experiment means what? What I've shown there is that the pressure drops then suddenly, just because of the, and it can sometimes increase as well, but the uniform conditions stop to exist after that. So that delta T over there on the right-hand side is your test time or available time. I'm moving too much, which is available to you to do experiments. How much is that time usually? That time is usually on the order of milliseconds, okay? Traditionally, it used to be a couple of milliseconds. Now we can extend it to longer times, but it's still on the order of milliseconds, okay? So one important thing that you need to do before you can study the fuel ignition is that you need to measure the speed of this shock wave, okay? So the shock wave is now in that figure traveling from bottom to up, okay? You put a bunch of pressure transducers, which tells you when the shock wave arrived there, and by knowing their distance, you can measure the speed of the shock wave. It can be anywhere from typical experiments from 400 to 1200 meters per second, okay? So that means it's supersonic. Could be Mach 2, Mach 3, Mach 4, okay? And so we need to know the shock speed because you can write some conservation equations. Sorry for the resolution, but you can write conservation equations of mass, momentum, and energy across the shock wave. And from there, what you see in these expressions is that in order to calculate the conditions, you need to know the Mach number of the shock wave and the gamma. Gamma is the ratio of the specific heats of the mixture. Okay? So that allows you to calculate the temperature and pressure after the reflected shock wave, which tends to be quite accurate, as has been verified by some laser-based experiments as well. And then what you also see is that we have some lens and a photodetector there, either through the side of the shock tube or through the end of the shock tube, and that helps us look at emissions, hot emissions or chemiluminescence coming from the shock tube, in addition to the pressure measurement. Okay. So then, what is ignition delay time? Ignition delay time is one of the key quantities that we measure in the shock tube, similar to the IQT that I described earlier. But what is the difference here? Now the ignition is only affected by chemical reactions. There's no physical process going on because I put the fuel as a gaseous mixture, fuel oxidizer, okay? So one thing to know, and it was probably clear before as well, but I want to make the point again, is that this release of energy is not instantaneous, okay? It looks instantaneous, but it kind of goes on exponentially after some induction time, and that induction time is what you are trying to get, and it depends upon temperature, pressure, and composition, okay? So again, in the shock tubes, this is a homogeneous experiment in contrast to an engine or an IQT, and this really depends upon the chemistry or kinetics of the fuel, okay? So my student here, Fatih, he really likes this description of the ignition delay time, so he asked me to share this with you as well, okay? So there's a kind of a legend which goes is that the inventor of the chessboard, right, when he invented it, the king asked him, "Tell me what you want, right? And I'll bestow upon you," right? And the guy was smart. He said, "Give me grains, put the grains in the chessboard, but keep doubling it." Okay? So put 1 in the first one, 2, 4, 8, and so forth. Okay? And the king was like, "Huh, that's it? That's all you need, right?" And he's like, "You should have asked for something big, right?" What the emperor or the king didn't realize is that it's going to if you keep doubling it, right, it's going to explode at some point in time, right? So what came out was that if you would have gone like that, it would have required 18 times 10 to the power 18 grains would have been needed to satisfy the wish of that guy, right? And that's actually even 1,500 times more than the current world population, right? And that was long ago. So what do you think the king did? Again, in the legend. What's that? Exactly, right? So he's like, you're like, go to hell, right? You tried to oversmart me, right? So he executed him, right? But anyways, so again, the reason my student likes this description is that he's like, this is how the wheat were exploding, and really you see the explosion towards the end as you reach the number 60 or towards the end of this chessboard. Likewise, this is what happens in an auto ignition process. You kind of stay in the black line, right? So sorry, yes, in the black line, right? You kind of stay low. You slowly release some heat, but then at the end, the system explodes and goes to explosion. Okay? So now, on a more practical front, this is how we measure ignition delay time in the shock tube. So what I plot here is pressure as a function of time. This because my cursor is not working, I'm moving myself. This first jump in pressure is the incident shock wave. Then the second jump in pressure is the reflected shock wave. Okay, so in this case, we are reaching a pressure of 40 bar, 40 atmosphere after the reflected shock wave. Then the pressure almost remains constant, starts increasing towards the end, and then it explodes, right, at around a little before 300 microsecond, 290 microsecond, and we call that the auto-ignition delay time, or ignition delay time of the specific fuel, in this case 2-methylhexane, at specific temperature and pressure that you see there. I can get the ignition from the pressure trace, or I can also get it from some emissions. So in this case, on the right, as I'm showing, you can measure the emission from the sidewall or end wall. Either you can look at OH star or CH star, which are indications of the chemiluminescence or the chemical reactions which are taking place. Okay. So then what we do is that apologize for the low resolution. What you do is that you perform these experiments over a range of temperatures. So this is then usually plotted on ignition delay time versus 1/T, and the temperatures are also there at the top. You can look at different pressures. You can look at different equilibrium ratios. And what you see is an expected behavior that we understand here is that the ignition delay time is inversely proportional to temperature, pressure, as well as equilibrium ratio, especially if you do the experiments in air. In some cases, in some labs, they do experiments diluted in argon or so forth, and then that equilibrium ratio dependence becomes a little bit more tricky, okay? And on the left-hand side, you see this really nice Arrhenius-like behavior of the ignition delay times as well, because in this high temperature region, higher than 1,000 Kelvin, the Arrhenius reactions or the chain branching reactions dominate, and I'll talk about that in a bit later, okay? The fuel that I'm using here is PRF91, okay? What does that mean? It's a mixture of 91% isooctane and 9% N-heptane volumetrically, okay? So this was just a specific example. Now, you see the longest ignition delay time that I'm measuring in this case is what? 2, 3, 4, 5, 6, 7 milliseconds, right? You see that on the y-axis? 6 to 7 milliseconds is what I'm measuring. And I'm getting down to pretty low temperatures, but not low enough. I'm getting down to maybe 700 or so. But if you want to focus on low temperature chemistry, we want to go to even lower temperatures where you would expect the ignition delay times to be even longer, okay? So how to measure longer ignition delay times? It tends to be difficult, as I said, with the shock tube. So one technique which is used is for extending the shock tube test times is we call it tailoring, or actually making the length longer. So that's why the tubes that you saw in the lab were sort of really long. One was 18 meters long. And that basically delays the two phenomena that I talked about before, either the impact of contact surface or the expansion wave. So in the black case, you see that we are able to reach much longer ignition delay test times. So this is just non-reactive cases on the right. So there's no ignition happening. So you see the black in this tailored condition gives us longer test time. So now in some labs, I think we have shown it that we can get to 50 milliseconds. In some other labs, they show that they can get to 100 milliseconds. But the point is that you can do this, but then some other challenges come into picture. Heat loss, some non-ideal effects start coming into the picture, and sometimes the tailoring is not perfect. So what is tailoring is that you mix helium driver gas with nitrogen with a heavier gas. And to do that perfectly is also not trivial, and so that affects the ideal nature of the experiments. Talking about some non-idealities, and that's why I had put inverted commas on my first slide, is one of the things that we observe in the shock tubes is that you have a gradual rise of pressure. You see that black line? Rather than staying along the bottom dash line, it's slowly increasing. And in this case, we are saying it's increasing by 2% every millisecond, okay? And that increase happens because the reflected shock wave comes and it interacts with the boundary layer, which was formed by the incident shock wave, and that sends pressure waves back to your test region, and so that causes an increase in pressure. So that's not good. Why it's not good in this experiment? Because I want to measure the ignition relay time at 20 bar and 995 Kelvin and not as a range of temperatures and pressures, okay? So that's a non-ideality, but we can take care of that in modeling, basically. And experimentally, it's very difficult. There are some strategies, but it's difficult. So in modeling, we can account for this change by having a volume history of this change in pressure, okay? But you need to really quantify how much is that. Is it 2% or is it 3% or so forth? Another non-ideality that we see in very few cases sometimes is that the ignition is not very homogeneous. So on the left is a high temperature ignition. So this is a chemiluminescence imaging from the end of the shock tube. So you see that it's igniting almost everywhere, kind of like what Bent Johansen showed for his HCCI engine. But on the right-hand side, you see the ignition starts from one side, and then it kind of expands. So that's another non-ideality that you would not like to have in the shock tube. So we try to avoid the regimes in which that happens, and we actually try to use that to our advantage to understand the pre-ignition processes, but surely that kind of process cannot be used to study the pure chemistry of the fuel or to validate our models.
What's the frame rate?
The frame rate in that case was 10,000. Yep.
100 microseconds.
Yep, 10,000 frames per second. So it's actually not that fast enough. Later on, we've done some work with, because in this case, we are using OH star, so it was limited by that. So we have done some visual imaging, then we can get to 60,000 or higher frame rates as well. So that's why it's kind of difficult to see the left one, right? Because it's just so fast. Okay, so don't worry, break is coming. We'll take the break at almost 10 o'clock, okay? So the other device, so that was about shock tube, and I'll come back to shock tube a little bit later as well, but the other device that we can use to measure ignition relay times is called a rapid compression machine. So this is a picture of the one that we have here. They come in a couple of different flavors. The one that we have here is a twin piston machine. So you have two pistons which come from the two ends by pneumatically compressing them, okay? And then there's a hydraulic locking mechanism which locks the pistons at their end position, as you see in the C part of that picture, okay? And so what you have then at the end, so as compared to an engine where you compress and then the piston comes back, here it does not. You lock it into place at the end. Now you have a constant volume operation, and so in that case, now you can study the fuel auto ignition, okay? The compression times for at least for the last 50% of the compression tends to be about a few milliseconds, especially in this device. Compression ratios can be varied, but here we were using we mostly used a compression ratio of 13, okay? This is just a zoom in of the combustion chamber, okay? And if you look at it more closely, we have those two pistons, okay, which are coming in, and then they're stopped there, okay? This is a zoom in of the combustion chamber, so that's the middle is where the combustion happens, okay? Then you have a pressure transducer on the left, and on the right-hand side is you have the valve for gas inlet and outlet, okay? So what is the how we measure ignition relay time in a rapid compression machine? So what you have here in red or in black as well is the compression here. So before time 0, the compression happens. The pressure increases to 10 bar in this case, okay? And then at around 120 milliseconds or so, you see the exponential rise in pressure, okay? So that's your tau is the ignition relay time, okay? But what we also see is a gradual decrease in pressure, okay? And that's something that I will talk about in a second, and that's a non-ideality of the rapid compression machine, okay? So then what is really nice is that you can combine the shock tube and rapid compression machine data. So the solid symbols here are the shock tube data. The open symbols are the rapid compression machine. In this case, we are showing data at 3 different pressures as a function of temperature. But the point that I want to really make here is that now you can cover a much wider range of temperatures. You can get to like 600 Kelvin or so, really long ignition delay times, like 100 milliseconds, okay? Well, whether those are relevant or not to internal combustion engines is a separate discussion, but definitely those data are very relevant to understanding the low temperature oxidation mechanisms of fuels, okay? So that's we combine the shock tube and RCM to study a wide range of conditions. So what about some non-idealities in the RCM? So one of the non-ideality, because compared to a shock tube, you don't have a shock wave, but you have an actual piston coming in, okay? So the piston comes in, and what you see in the bottom half of the picture, so this is a kind of a complicated picture, so what we're trying to show is that what if you have a flat piston, which is the case in the bottom case, then the boundary layer will sort of be scooped in by the piston, okay? And then you make this roll-up vortex. And that's not good in this experiment. Why? Because it's going to cause inhomogeneity, both concentration and temperature, so that's not good for a chemical experiment. What you can do, though, is that you can design a crevassed piston. That's shown on the top half of that picture. Again, doesn't mean that you have half piston is flat and half is not, just to show it graphically. In the top half, you have a crevice piston. So the crevice is that volume that you see behind the front face of the piston. So if you design it in a nice geometry, what it will do is that as it comes in, it will sort of absorb the boundary layer in that crevice volume. Okay? So you have to design it nicely so that it doesn't cause more inhomogeneity, but it can squeeze in the boundary layer in there. Okay? So okay, so that was one issue, the vortices. So you can take care of that by looking at by designing crevice pistons. Another problem that I alluded to earlier is that you have a heat loss. Why do you have so much heat loss in a rapid compression machine? Because it's a small volume. Okay, so the surface to volume ratio is not very favorable. So you have a heat loss as a function of time, and also you are looking at long times. Okay, so you look at that that dashed black curve, which we call the non-reactive. Okay, and so it's going down as a function of time. That's because of heat loss. The pressure is going down. If there were no heat loss, then I would get this solid black ignition. That's when the ignition will happen. But because of heat loss, the ignition happens much later. Okay, so it's almost actually the ignition layer time changes from about 20 to 60 milliseconds. Okay, so what you do is that, again, this is the nature of the device. You can't really overcome that. So you try to account that by measuring the non-reactive traces. And so with that, you can model. You can include this in your modeling. Okay. So that's what we call the adiabatic core hypothesis. Okay, so you assume that your core is adiabatic, okay, and you have done a good enough job of absorbing the vortex and the boundary layer, and then you can apply the isentropic expression. Okay, so you can use the isentropic expressions to calculate the temperature at the end of the compression, which is shown here. Then by measuring the pressure, and then you can use that to characterize. Calculate the volume history, and with the volume history, you can know how much is the heat loss and include it in your model. Okay, so that's how you kind of model an experiment in an RCM. Again, it's not as ideal of an experiment as a shock tube, but it still provides us very valuable data. Okay, I think it's probably a good time to take a break because I'm going to talk about a little bit more in detail of what you get from this. So any questions before we go for a break? Yes.
Hang on. How dare you ask a question without the cue?
Yeah, how will you characterize the validity of using chemical equilibrium assumption for hydrocarbon gaseous fuels like natural gas and propane? Perhaps?
Chemical equilibrium?
Yes. You showed a graph beginning of the something.
Oh, okay. In the beginning, right?
Yes.
Okay. So that's basically the answer is time scale, right? So if any chemical system, if you wait long enough, right, then the transients will go away. Okay, the kinetics will go away, and eventually everything will be dictated by equilibrium. Okay, and in that case, it's dictated by thermochemistry. Okay, of the system. So I think it depends on whether you want to look at a system in steady state. Okay, once it has reached steady state, then equilibrium will surely what will dominate, right? So, for example, in the context of an automobile, what comes out at the exhaust, right? Okay, of the tailpipe of the car, that's primarily because the long time has passed, and that's dictated primarily by the thermodynamics or by equilibrium, right? But what if you want to know what is happening as piston is moving inside the engine, right? That's transients, right? So that's then you have to describe the kinetics in that case. So it's really a time scale question. Okay.
Anybody else?
Any more?
Oh, here we have one. Marina.
So can you always calculate the CDN number that's from the measured ignition delay in shock tube or RCM? Can you find that out?
Okay, that's a good question. So we've been looking into that for quite some time on what is the the relationship between ignition delay times that you measure in shock tubes or RCMs, which we call homogeneous ignition delay times. How do those relate to an octane number that you measure in a CFR engine or a cetane number that you measure in an IQT, for example, right? And the short answer is that yes, you can relate those, okay? You have to choose specific conditions, okay? You have to choose what has been done a lot in Mani's group and at Saudi Aramco is that they've looked at a wide range of ignition delay conditions and then see where do you get the best correlation of octane number with the ignition delay time. The condition has been found to be for RON at least around 820 Kelvin, 20 atmosphere, okay? So it doesn't, all the ignition delay times don't correlate to RON and MON, but at specific conditions it may be able to, okay? But I don't think the story is complete, okay? Because the process in a CFR engine is still very different than what is happening in a shock tube or in a rapid compression machine, okay? So in a CFR engine, your fuel is going through a series of positions or a series of temperature and pressure thermodynamic conditions, right? So to correlate that to one condition in a shock tube or RCM is, again, there is some validity to that, but it's not as exact as we would like it to be. A very good question. Okay, so maybe we can go for coffee and be back in 10 minutes?
10 minutes.
Okay, back at 10:10. Okay. Okay. Okay, guys. You had a 20-minute break. Okay, I'm going to make the quiz even tougher because of that. Okay, should we get started? Okay. So just before the break, we were talking about the ignition delay time measurements in the shock tube and in the rapid compression machine. Okay. So I want to show you some interesting data that we have obtained from shock tube and rapid compression machine combined. So what I'm plotting here is the ignition delay time, again, as a function of inverse temperature here, or temperature on the y-axis, for 8 different gasoline fuels, okay? And you see that this is done at phi of 1 and p of 20 bar. And these 8 different gasoline fuels have very different octane numbers. So you can see some have 70, 80, 90, okay? So that means they are going to behave very different in the engine. What also is written is the S, sensitivity of these fuels. What is sensitivity is the difference of RON and MON, RON minus MON. And also these fuels have very different sensitivities. Some have about 0 sensitivity, and some have sensitivity as high as 11, okay? So very different fuels, both in their RON and MON, but also in their chemical nature, chemical composition, which we have checked from doing DHA, okay? So we know they're very, very different. But what you see really interestingly is that high temperatures, like higher than 1,000 Kelvin or 950, they all have very similar ignition delay times, okay? Almost identical ignition delay times. Then once you go to lower temperatures, and in that region, what we call the NTC, negative temperature coefficient region, you start seeing some separation between these different gasolines. And then at the very low temperatures, again, you see some separation. So we see that the composition dependence or the RON-MON dependence is negligible at high temperatures. You see it predominantly in the NTC, and then relatively weak dependence at low temperatures, okay? So why is that happening, okay? Why are these fuels, which are so different from each other, behaving almost same at high temperatures? So that can be explained by basically looking at how fuels oxidation happens from a chemical nature or chemical oxidation perspective. So you start with the fuel at the top, okay? So in the high temperature part of the mechanism, basically what dominates is pyrolysis reactions, followed by which lead to making small hydrocarbons, and then their oxidation happens, okay? And that process, that fast high temperature oxidation or ignition process beyond 1,000 Kelvin, really doesn't care about the nature of the fuel, okay? Almost, especially once you have a mixture of a lot of components, they will all ignite together in a very similar fashion, okay? But once you go to the low temperature pathways, okay, that's when you add the oxygen, you make RO2 peroxy radicals, you make add another O2 to make QOH radicals, you go through another chain branching pathway at low temperatures. That entire pathway is very much dependent upon what is the nature of R that you started with, or what is the nature of the fuel that you have there, okay? And then we have our sort of intermediate temperature pathways there, okay, which is where you have now the competition between whether the RO2 going to the chain branching pathway or going to some elimination pathways or not chain branching pathways. And that competition is what gives you the NTC region, okay, the negative temperature coefficient region that we saw also on the ignition delay curve on the last slide, okay? So again, what I wanted to highlight here is the high temperature ignition is for all practical fuels, for all practical purposes, is very similar. We see the differences in fuels only at as we go to lower temperatures. Okay. The chemistry is at high temperature and low temperature is very different. Again, at high temperature you have the pyrolysis and then followed by oxidation. At low temperatures you can also say it's oxidation followed by pyrolysis, but it's very different. You have the O2 addition, RO2, and then this is not a two-step process, it's a multiple-step process on the low temperatures. It depends a lot more on the chemical nature of the fuel. Okay, so I'll just quickly, without going into the details of this, point out a lot of work that we've done on surrogate formulation. I know Angela will talk a lot more in detail about the surrogates later in the afternoon. But what we were able to figure out is that for a variety of gasolines, what kind of simpler representation you should use. And we categorized that in terms of the sensitivity of the fuel. Again, S is Ron minus Mon. And we saw that for very low sensitivity fuels, irrespective of their Ron and Ron numbers, you can use a PRF, two-component surrogate, to describe the ignition of that fuel. If you have a medium sensitivity, then you need to add toluene to basically compensate for the sensitivity. And then for very high sensitivity fuels, you need multi-component surrogates. And for that, we have a very nice tool here in our center, which you can use to, you can put some target properties, and then it will help you come up with a multi-component surrogate, which represents the real fuel. And you can try this tool and many others at the CloudFlame portal. Okay, so that was all about ignition delays in the shock tube and RCM. Any questions on that? Okay, so that, again, I want to, at that point, the high temperature ignition of all practical fuels being very similar is something I want to just take home message from that part is very important. Okay, another kind of experiments that you can use to characterize the chemical nature of the fuel are laminar flame speeds. And I know Professor Maruta talked about this in detail in his lecture on the first day, so I will not go into the detail of this, but the point here is that this gives us an additional measurement that you can use to validate your mechanisms, okay? It depends not only now on the chemistry, the high temperature chemistry, but it also depends on the transport properties of the fuel, okay? So you have different methods for measuring the flame speeds, burner method, flat flame, and then this is the method that we use in our center, and outwardly propagating flame. So this is a schematic of the experimental setup. So you put your premixed fuel and air mixture into the spherical vessel, then you ignite it in the center, and then with Schlieren photography, you can measure the speed of the expansion of the flame, and making some corrections, you can get the flame speed of the mixture, okay? So I just show some typical data here. On the left, I plot flame speeds, laminar flame speeds as a function of equivalence ratio for 3 different fuels, dimethylfuran, ethanol, and gasoline. And then, as some of us know, is that the ethanol has much higher flame speeds compared to typical gasoline, and DMF, dimethylfuran, is very similar. Flame speeds also depend upon temperature, okay? So on the right, you see fuel is not written there, it's propene. So we are looking at the flame speeds of propene at 3 different initial temperatures, okay? So you see that the higher the temperature, the higher the flame speed is, and it depends on equivalence ratio. Also, we can perform experiments, look at the pressure dependence of the flame speeds, and that's also something that should be modeled by the mechanism that you have. Was there any question? Yep. Good question. I think he's saying, what is the temperature and pressure for the plot on the left? because he's right. I have not listed there. I think this was room temperature. No, I should check that and confirm. Yeah. I think are the units are no, okay. You see on the it's for the which one are you saying doesn't look right?
Left side's too fast.
And maybe it is higher because for gasoline you need higher temperatures to evaporate it. Might be. I will check that. Yeah. Good. Thank you for asking that. Good question. That's what I like in the class. Yeah. Okay. Any other questions on flame speed? No? Okay. Other than that one. Okay. The other device that we use for testing our models, and we have a very nice setup for that here is a JSR. Okay. So what you do here is that you have your reactants coming in from the top. Okay. And then you create some sort of this jet structure, okay, in the middle to create enough mixing, okay, so that you can have a well-mixed design. Well-mixed fuel air mixture. And I was just talking to one student in the break is that, a lot of work has gone down into designing these jet reactors and then using some measurements to make sure that you get enough mixing, and then you can look at the chemistry under those mixed conditions. Okay, so this is a more detailed experimental setup that is used here to study a jet-stirred reactor, oxidation in a jet-stirred reactor. The JSR is there in the middle. It's put usually in a furnace, okay, so that you can heat it up and then study the oxidation processes at different temperatures and pressures. Okay. And then usually you use a GCMS kind of coupling to it, although it can be coupled to more advanced diagnostic methods as well to look at the speciation. So primarily you look at speciation coming out of the different species coming out of the exit of the jet reactor. So there are many different designs, again, as I was saying, people have looked into, okay? The configuration of the nozzles, the number of nozzles, the angle of the nozzles, and so forth. And then you can do some validation studies, some tracer-based studies to look at which design is better than the other. And then some work was done here and other places to verify. The most famous design is the Philippe Daguerre design that is used in many different places. Okay. So what you can measure from JSR is these kind of quantities. So in this case, I'm showing oxidation of N-butanol and N-heptane mixtures. Okay. So you can measure mole fractions as a function of temperature. So you can change the temperature with the furnace. On the top, we are plotting in the green the N-heptane, N-butanol, and then formaldehyde. Okay. So again, just like the ignition delay curves, you see the two-stage ignition, or the low temperature and then the NTC and then the high temperatures towards the end. Then you can measure some intermediates shown on the right, ethylene, methane, propene. You can measure the products of the combustion and so forth. So and the lines here, the dots are the experiments, lines are the model comparison. So it just provides a lot more data. So compared to a shock tube and RCM, which just gives you one measurement in ignition delay time, which is like a global reactivity parameter, a JSR-like study gives you a lot more information on the species, which can really help fine-tune the chemical model that you have put together. Okay. Now flow reactors, moving on to the other devices. The flow reactors, they come in different flavors, okay? So this is an example of the Princeton's turbulent variable pressure flow reactor. So for a turbulent reactor, what you make sure is that you have enough mixing in the early part of the reactor, okay, through turbulent processes, so that then you can go ahead and model this as a plug flow reactor, okay? So the total residence time in that case can be broken down to your initial mixing time, or the perfectly stirred reactor time, plus the PFR time, okay? And so if the initial mixing time is small enough, then it becomes relatively easy to model what happens in this turbulent flow reactor, okay? Now, if you talk about, and I'm not showing you some examples of data from here, but basically the data that you get out of these flow reactors is also speciation. So you couple it to GCMS kind of devices, and then you can look at as a function of temperature and pressure, because this can go to really high pressures, what happens to chemistry at high pressures. Once you go to laminar flow reactors, as we know, what happens now is that if you look at that picture in the black, now you have a velocity profile there, okay? So now the problem is that you will have some, because of the velocity profile, the composition and temperature will not be uniform, okay? So then this has to be modeled very, very carefully, and it's not as easy. And I take this nice picture from Peter Glarbog's paper, where he shows that under what conditions you can model the laminar flow reactor as a perfectly as a PFR, right? So what he plotting here on the y-axis is a dispersion coefficient, and on the x-axis we have the Bodenstein number or the Pecklet number. Okay, so well, it could be done as a Pecklet number. So this is a product of Reynolds number times the Schmidt number. And what he shows is that based on this pipe flow kind of diagram, just in the valley of that picture is where you can model this as a PFR, okay, as a perfectly PFR in your modeling, okay. So once you make sure that you are in that condition, then you can go ahead and perform very nice experiments in laminar flow reactors as well. So this is an example shown here. So you have the inlet coming into the reactor, and at the outlet you measure the species, okay. So you can do this at different temperatures and at different pressures as well. You can couple this again to a GCMS or couple it to a more advanced methods, which I will show on the next slide. So in this case, we are looking at indene, a very important precursor for soot formation. Again, Angela will talk in detail about pH and their soot formation process later in the afternoon. So that then can be used to look at the pH or soot formation mechanisms if you measure those kind of species. The temperature profile on the left-hand side, you see, is not uniform in this reactor, so that also has to be taken into account once you model this. So it's not as ideal of a device, but still provides us valuable data. What you can do is that, this picture shows is that coming out of this quartz reactor, so usually you use a quartz reactor, you can use some sort of ionization method, either an electron ionization or, in this case, a molecular beam, a synchrotron-based vacuum laser-based ionization, and then you can use a mass spectrometer to look at at various species. And what is really nice about this technique, which was initially used for low-pressure flames, and really Craig Tadgis at San Diego National Lab led a lot of the earlier work with this synchrotron, ultraviolet, photoionization mass spectrometry, you have the ability to separate out the isomers, okay? So you can vary your photon energy, as you see on the plot in the left, and by looking at what photon energy you get the signal, you can separate out different isomers, okay? So they have the same chemical, which you will not be able to do if you were doing like a regular mass spec or a GCMS kind of detection, okay? So that's really the power of this technique, is that you can look at much more details of the chemical nature or isomers coming out of the oxidation or pyrolysis process. Okay, any questions? Okay, so I get to now, Bob was getting ready. Any questions? Okay, so we get to now, so we started with a very high-level chemical experiment, which was the shock tube experiment. High level in the sense that it gives you an auto-ignition delay time, okay? Now we went through some other experiments, like a laminar flow reactor, a turbulent flow reactor, a JSR, which are then used to look at more details of the chemical process. But still, they give you the speciation, okay? What would be really nice, actually, is to be able to look at each elementary reaction, because that's what comprises the overall model that we have, okay? So I give this example of this reaction CO plus Cl2 making COCl2. By the way, someone knows what is that compound, COCl2? Yeah, another name for it? Phosgene, right? And phosgene is used in, I think, pharmaceutical companies as well, so it's produced quite a bit for that, but it has a like a bad memory in the sense, was used quite a bit in World War II, right?
World War I, Adolf
World War
Hitler
I. World War I,
was
sorry.
himself by that. And
that's right, yeah.
That's why he became so angry.
Yeah, so it was used, so it's very poisonous in that sense, okay? So Anyway, so the point here is that, and usually you need actually some sort of catalytic process to make that conversion happen. But the point here is that for this kind of a reaction, you can write the rate of, for example, the decay of CO, so dCO by dt, which is just, I'm writing the law of mass action, okay? So that depends on K, the concentration of CO, the concentration of chlorine to the power half. Where does that half come from? That comes from experimental observation. But the reaction does not proceed as it is written. It actually proceeds through a bunch of elementary reactions, okay? In this case, these 4 reactions describe the chemical process or the mechanism which is happening. So Cl2 dissociates, gives you 2 chlorine atoms. That then reacts, combines with CO to give you COCl. That reacts with Cl2 to give you COCl2 and then a chlorine atom, which can then combine to make Cl2, okay? So that last one would be, in our earlier description, would be a termination reaction, okay? 2 Cl radicals coming together and making Cl2. So what we really want to do it is that to describe this formation of phosgene, okay, we need to be able to know these 4 reactions really well. We need to be able to know the rate constant of each of this individual reaction, and then we can describe the mechanism. So these individual elementary reactions that we have, they come in different flavors, okay? So they come, you can have a unimolecular reaction, so just some A going to products. You can have bimolecular reactions, A plus B coming together giving you either one or many products. You can also have sometimes termolecular reactions, okay? Why did I not keep going? Why not 4 molecular, 5 molecular reactions? The probability, right? The statistical probability of that happening is very low. Even for termolecular reactions, it's not as common of reaction classes as bimolecular reactions, okay? Okay, so what I've written there is then the law of mass action for these. And again, what we want to know is the rate constants K1, K2, and K3 for these kind of reactions. So one device that we use, at least in our lab, to measure the elementary reaction rates is again the shock tube, okay? So the shock tube can be used to measure the autoignition delay time, which I described earlier, but it can also be used to measure these elementary reaction rates. In this case, you make use of some laser-based diagnostic. So what we are doing here in this specific case is we want to detect OH radicals. So we start with a pump laser at 512 nanometer. We pass it through a ring dye laser, which gives us a visible laser at 630 nanometer. Then we frequency double it to get a UV light coming out of that wave train at 306 nanometer. Then we make it pass through the shock tube. We measure the intensity before the shock tube, so I naught, and then after the shock tube. And then we can combine those 2 intensity measurements in what is called the Beer-Lambert law to calculate the mole fraction of OH radicals in this case. So that 306.7 nanometer is in resonance with an OH absorption feature, okay? So in this case, the objective was to measure the reaction of fuel plus OH. So fuel could be anything. Fuel could be methane, could be toluene, N-heptane, or could be more complex mixture. But we would rather like to use a single component fuel. And then we want to know what is the rate constant of that reaction fuel plus OH. But then how do you get OH in the shock tube? Because we don't want any other things in there. So we use a thermal precursor. It's called tert-butyl hydroperoxide. What happens there is that bond between O and OH is very weak, has low bond dissociation energy. So that breaks off very quickly as you heat, as the shock wave heats the mixture. And that gives you an OH radical, which can then go and react with the fuel. You get some extra stuff, that butoxy, which you don't want, but you can take care of that, okay? So then it's very important to isolate the reaction. So we want to just measure the rate constant of the fuel plus OH reaction. So what we do is that we can do some sort of sensitivity analysis. We have some other tricks as well, but in this case, the sensitivity analysis tells me for this specific case here where I want to measure the rate constant of IC4H8, which is isobutene plus OH, is that the sensitivity of OH to this reaction is highest, and then there is the 2 others are close to 0, right? So those which are close to 0 will not affect the OH concentration as much. Okay? So then with that information, I go ahead and perform the experiment in the shock tube, and I can measure that OH mole fraction, which is shown in those dots, black dots, as a function of time using the diagnostic. And again, what am I starting with? I'm starting with that OH precursor and the fuel, okay? So then you can basically either just plot it on a log scale, which I didn't go into the detail of that because we are doing it in pseudo first order regime. And from the slope of that, you can get the rate constant K, or what I'm showing here is that in this case, we do a model fit to it, but the best fit, the red line, is what gives me my rate constant, okay? which in this case is measured to be 1.18 into 10 to the power 13 centimeter cube per mole per second. And so the two dashed lines show the sensitivity, okay? That means that I'm really sensitive to this reaction, and that helps me get the rate constant, okay? So once I have that rate constant, so that experiment is at a specific temperature here, as written at the bottom at 1120 Kelvin. I can repeat the same experiment at different temperatures in the shock tube. So then I can plot the rate constant as a function of inverse temperature for that specific reaction, isobutene plus OH. The black dots are the measurements, okay? And then we are comparing it with some models, the dashed line and the black line, and then also comparing it with a measurement for another fuel, propene plus OH, which tends to have less rate constant than isobutene plus OH. But what you see is that black solid line, and actually some of our data also show now that at lower temperatures, you start deviating from the Arrhenius nature, okay? So rather than having a purely Arrhenius nature, you start seeing some non-Arrhenius behavior. And actually what happens is that the OH at lower temperature, rather than abstracting an H atom from isobutene, it starts to add to the double bond, okay? And that addition process has very different physics or chemistry to it than the abstraction process, which is primarily what we studied here. Okay, so how does this reaction actually take place? So now we are going to really details of the elementary reaction. So we have an OH radical at the top coming in and attacking this isobutene, okay? So just for simplicity, I also show the isobutene structure down there, okay? So now that OH can abstract an H atom, basically knock off an H atom from one of these two sites, either from the CH2 site or from the CH3 site, okay? And that CH3 site is called an allylic site, and this one is called a vinylic site. So that's what you see in those two channels, either the channel 1A, where it was removed from the CH2 group, or the channel 1B, where the H was abstracted from the CH3 group. Now, these two are sort of two sub-channels of the overall reaction. And why would I want to know the rate constant of these two sub-channels, K1A and K1B? It's actually very, very important, because what happens next to that radical at the top or the radical at the bottom is very different. The allylic radical that we have formed there is very stable. So it persists for long periods of time in your combustion system, whereas the vinylic radical is much more sort of reactive. So this distribution between these two radicals is very important to predict the overall oxidation of this entire system. But then how can I get it? How can I measure K1A and K1B? Because the only measurement that I showed you was just the OH, and OH is used in both channels, okay? So how can we do that? The way we do that is by method known as DKIE, was really put into practice a lot by Frank Tully at Sandia National Labs. So you deuterate your isobutene, meaning you ask a chemical supplier that give me an isobutene, but now replace the H atoms with some D atoms, okay? And these tend to be quite expensive, these deuterated molecules. So you deuterate it selectively at different sites, as shown here, these three molecules, okay? So that basically then provides you more, if I just say in simple words, additional information for detecting what happens at these two different sites. So then you can go and, in the shock tube, perform now experiments on these 4 different molecules. And what you see is that once you deuterate the molecule from isobutene pure to different levels of deuteration, the rate constant decreases. So the one which has 8 D atoms compared to the one which has all H atoms, the blue is the K4, has the lowest rate constant, okay? So by combining this information of deuterated, and the reason that happens is because of the 0-point energy of the deuterium-based system being different from the original H system, okay? Well, anyway, so we use this information then to look at the branching of the two channels, and then eventually we can get the branching ratio, meaning how much of the reaction goes to the allylic channel versus vinylic channel, and then we see that this branching is a function of temperature. Primarily, the allylic channel is dominated because of the lower bond dissociation energy there, but still the vinylic channel plays an important role. Another method, which is used for quite a while for measuring the elementary reaction rate constants to building up the models, is a combined flash photolysis plus laser-induced fluorescence experiment. So what you do in this case is that you don't use a thermal source, like we were using the TBHP. Here you have some other source for H atoms, like maybe H2O2 you can use. And then you use a really high energy pulse of an excimer laser at 248 nanometer that basically dissociates it to give you 2 OH radicals, which can then combine with your fuel, and you look at the decay signal using LIF, laser-induced fluorescence, as shown in that black over there. And then you do this at different concentrations, different reactant concentrations on the right, and from there you can calculate your pseudo first-order reaction rate constant. So this is an alternate method, and usually it is used actually at lower temperatures. So shock tube is used at higher temperatures to get the elementary reaction rate methods, and this method is very good to get rate constants at lower temperatures. Okay, so that kind of ends the third topic of the presentation. Okay, so now is a good time to ask questions. Anyone? Or should I ask questions to you guys? Yes, Professor Marud.
Regarding the sensitivity, Ramon,
yeah.
Is it possible to provide sort of the physical or chemical interpretation about S?
Yeah. So I think there's some work from Lawrence Livermore National Lab has shown that the sensitivity can be related to the slope of the NTC region, right? So if I plot the ignition delay times, right, which is, again, I'm looking at ignition delay time as a more of a fundamental description of the fuel, and then you can see the sensitivity as a slope of the ignition delay time. But more than that, the sensitivity is related to, for example, if I have alkenes now, okay, so if I have double bonds in there, okay, those double bonds, the way they affect the bond dissociation energy affects the sensitivity of the fuel. So alkenes tend to have higher sensitivity than alkanes, okay? So it's related to the to how basically easily you can go through the degenerate low temperature chain branching pathway or not, right? But once you start making the alkene longer, right, then its sensitivity starts dropping, right, because it doesn't behave as like an ethylene or propylene will behave. So yes, the short answer to your question is that the sensitivity can be related to the chemical nature of the molecule.
Can you put up your deuterated compound again?
Yep.
I just want to make it clearer in your head. What he's speaking to is when you put the deuterium and replace it for hydrogen, and it turns out 1% of all the water we drink has deuterium in it. So there's a lot of deuterium. 1% of all hydrogen is deuterium. And the deuterium is twice as heavy. It has a neutron in addition to a proton. And the net result is the reaction rate is lower by 2?
Something like that, yeah.
Something like maybe 2. And a consequence of that is if you were to drink D2O instead of H2O, you will die. It's that much difference to your body. The reaction rate of deuterium with everything else in your body is slower by a factor of 2, and that's a killer. That's amazing. So this is a very clever technique pioneered over the last 100 years, but with increasingly better spectroscopy and all that, you just keep coming back to this old technique that's extremely valuable in trying to unravel things. Very important.
Thank you.
Yeah,
okay. Anyone else? Yep.
Great question. Yeah.
Okay, so when you talked about the laminar flow reactor, you told you use a quartz reactor.
Yep.
Is that a specific reason for that, or?
Just inert, right? So the inertness of quartz versus if I would use stainless steel, right, then you can have more wall reactions taking place, right? So quartz is a good inert reactor.
Yeah, but it's like more fragile. So
sure. So you have to be. So if you want to go to higher pressures, then then it becomes tricky, right? So most of those laminar flow reactor experiments are either done at sub atmosphere, like a few hundred torrs, or at atmospheric pressure. Going to higher pressure becomes tricky then maybe you have to put it in kind of balance out the pressure from inside and outside. There are some people use that technique, right? Okay. So they will have some other flow outside to balance the pressure. But yes, definitely that it's more difficult to do high pressure experiments.
Okay, thank
Sorry.
you.
But I think high pressure meaning that if you want to go like 10 bar, right? Then the delta is 10, right? But if you go to like a few hundred torr, right, compared to an atmosphere. Maybe give it here. Yeah, please explain. Yeah.
Even professors have to use the box, okay?
Sorry, I forgot. So I believe that if you go to the lower pressure, it's tricky because the collision frequency between the gas molecule and gas molecule with wall would be, which is it? It's low pressure, the wall effect would be larger.
Sure. Well, I think for that you have to go like really, really low pressures, right? For that to see. Like depends again on how many wall sites you have and how many collisions. So you probably will have to go like sub-torr, no? For that to become dominant.
All right, so just general.
Yeah, but generally you're right. Yes, absolutely. But I think her question was more on the fragility of that quartz reactor.
Oh, I see. Okay.
Yeah. But no, in general you're right. The wall reactions will become more important at low pressures. Yes, there's one more there.
Where is it? Oh, there it is.
Thank you. When you talk about to determine the elementary reactions on the mechanism, you are making the supposition that only one reaction on the whole mechanism dominates the OH absorption.
Yes, so yeah, very good question. Yeah.
What is happening when you have two reactions that has high sensitivity on that for that species?
Yeah.
Or, for example, when you are making all the temperature change, you are supposing that this reaction is the only reaction that is important. Maybe this reaction, when you change the pressure or temperature, change of the relative importance.
Sure. So good question. There are 2 points here. One is that how do we determine what reactions are important in a mechanism, right? And then how do we sort of down select from that what reactions do we study with these kind of techniques, right? So you're absolutely right. It depends on what is the condition, right? So for example, if you're at high temperatures, as I said earlier, maybe it's just H plus O2 going to H plus O is what dominates, right? And then some pyrolysis reactions which happen very early in the scheme of things. So you can look at the various sensitivities, right? And from there you can see what reactions are dominating. And there are some much more advanced tools now to do that. You can do like CSP analysis. Professor Hongem does here, okay, to look at the explosive modes and so forth. So with these sensitivity analysis, rate of production analysis, CSP and so forth, with these methods you see in this big mechanism that has maybe 1,000 reactions, what are the key 5 or 10 reactions at that specific reactor condition, okay, or for that specific application. Now, once you have determined that, then you say, can I come up with a method to determine the rate constant of this critical reaction, right? Can I do a detailed theoretical calculation, or can I do a detailed experiment like this one, okay? So in this case, what I'm showing is that we had figured out that this fuel plus OH reaction is very important, okay? So we made that determination initially. And then we say, how can we measure the rate constant of this fuel plus OH reaction, right? So we then try to design a system, an experiment, where we will be only sensitive to this reaction, okay? Because we have predetermined that this is important, right? So, okay. And now even here we see that there are a couple of other reactions which are affecting the OH concentration, but their contribution is much more minor than your key reaction, right? So then it works like a very good setup or experiment to help me unravel this specific rate constant, right? So it's kind of a 2-step process. First step to determine what reactions are important, and the second step to see how can I more accurately get the rate constant of those critical reactions. Does that answer your question?
Yes, thank you.
Regarding the jet state reactor, is it only used for partial oxidation of the fuel, or it can be used for full fuel oxidation because of the fragile nature of the reactor?
So you use you can use it for full oxidation as well, but what you use is use highly dilute. Okay, so you use really dilute mixtures in the GSR. Okay, so you don't want, and also you control your residence times. Okay, by controlling the flow rates. So with those, you keep the energy release to a minimum, right? You try to keep it more, do it more like in an adiabatic fashion. Okay, so but you're absolutely right. If you were doing like a fuel-air kind of mixtures with very high concentrations of fuel, then it would just explode, right? So you do it at very dilute conditions.
Okay, thank you.
That's a good question. Okay,
I think we're
can
good.
move on.
Yep.
Okay, all right. So we go to the last part of the course, which is how can you make use of some more diagnostics to unravel further things about the chemistry of the fuel, or unravel what is happening in these devices. Okay, so I've listed here 5 techniques: absorption spectroscopy, thermometry, cavity enhanced, mass spectrometry, and microwave. And this is by no means an exhaustive list. This is probably the diagnostic techniques that I like or I have used. Okay, and actually in the interest of time, I'm only and not to overwhelm you, I'm going to only talk about the first 3 here. But the 4th and 5th one are also very important. Mass spectrometry, I've kind of talked about it a little bit before, especially when you do it at a synchrotron-like facility. It can provide you really a wealth of information. Microwave spectroscopy has been used quite a bit in the past, but recently there is some nice work from Sandia National Lab showing that it can also be used to get additional information about species that you may not be able to detect otherwise. Okay, so we will focus on the first 3. Okay, so absorption. It's probably the simplest of the laser diagnostic techniques. Okay, but then very useful and very can provide you really quantitative information, which is sometimes tricky with other techniques. So what you do here is that, and I alluded to this earlier when I was talking about the OH absorption. So you have a laser, and you normally have to use a narrow line width laser, meaning that it's spectrally narrow. So you pass it through your gas sample, and then you look at the ratio of the transmitted IT to the incident intensity, and then that is related to these some parameters, some spectroscopic parameters. S is the line strength of the transition, phi is the line shape function, sigma is the absorption cross-section, and n is the number density. What do I mean by line? A line is an absorption transition between an upper quantum state and a lower quantum state. Okay, so that's and has some width to it because of the, on a simple level, Heisenberg uncertainty principle, or because of the collisions that happen. Okay, so basically what you do is that by making the measurement of IT and I naught, and by having some information of these spectroscopic parameters that we have here, like S and phi, and knowing the pressure and the length over which that's happening, you can get the mole fraction. Okay, so it's a very nice quantitative technique to measure the mole fraction of species. Okay, so its pros are that it's let's move my cursor here. That it's non-intrusive. You can reach really high time resolution. The really big con of this is that it's path average. So it will give you a measurement over the entire path length L, an average measurement, which is okay in homogeneous systems, like if I'm in a shock tube or in a rapid compression machine, but it will not be very suitable for flame-like experiments where you have a lot of inhomogeneity along the length of the laser. Okay? So just to kind of go a little bit fundamental aspect of this, what you are trying to do here, for those of you who are not familiar, you start with a ground quantum state, and you choose an appropriate photon energy or an appropriate laser wavelength, okay, that will make this transition from ground to upper electronic state. Now, depending upon in which region of the electromagnetic spectrum you are, you may be only perturbing the rotational levels, so then we'll call it microwave region. You may be perturbing or making a change in both the rotational and vibrational energies of the molecules. Okay, so then that gives you the infrared spectrum. Or once you do also make changes to the electronic nature, meaning moving the electrons, right, from one shell to another, then that gives you the ultraviolet region. So you can use lasers in different regions to do absorption spectroscopy for measuring the mole fraction or other quantities of interest. Okay. So what we do a lot here, at least in KAUST, is that we do most of our work in the infrared region, but I should just give you an example of measurement of OH in the ultraviolet region, okay? Because the ultraviolet region tends to give you a much higher sensitivity, especially for radicals. But for molecules, it becomes more cluttered, and it's easier to separate them in the mid-infrared, okay? There are some databases that you can use to get the S and Phi parameters, the spectral parameters. So it's HITRAN and PNNL database are very useful to look up the spectra. So this is an example of a concentration or mole fraction measurement through the shock tube. So in this case, we are starting with a quantum cascade laser at 4.2 microns. We are making it pass through the shock tube. So obviously where the light is passing through the shock tube, we have a quartz window there, or actually in this case a sapphire window, because quartz does not transmit at 4.2 micron. And so then we collect the laser light on a photodetector on the other end, okay? We look at the spectra, simulated spectra of CO2 in this case on the right-hand side as a function of wave number, and we pick a specific transition or a specific wavelength at which we want to do the measurement, okay? So there's a lot that goes on in choosing what wavelength in that entire region is best for making this measurement, and that depends on a lot of factors. So this is an example measurement that we made of CO2 mole fraction in the shock tube because our target was, in this case, we wanted to look at the very important CO plus OH reaction, but at conditions at which it had not been explored before. So this is the main energy release reaction. Okay? So if I have to put it as, it's probably one of the top two most important reactions in combustion. So CO plus OH gives you CO2 plus H. So here we are looking at the formation of CO2 in black, and then again, by doing some modeling, we can get the rate constant of this reaction. But what is to be, the attention that is to be paid is that the amounts that we are measuring here are in parts per million. Okay? So these are very small amounts, starting from a few ppm to 25 ppm. So you need a really highly sensitive diagnostic to be able to make these kind of measurements, and that's what the mid-infrared and quantum cascade lasers give us. The next thing that you can do is that you can also measure temperature, and temperature is obviously a key parameter in any combustion system. So the way you can measure temperature is by a method called two-line thermometry. Okay? So in this case, you make advantage of the fact that if you choose two transitions, two different wavelengths, the only thing and then you take the ratio, all other quantities will cancel out, and then the ratio can be used to measure temperature. So I show there that if I measure R, the ratio, the areas of two transitions, integrated areas, then it only depends on S, the line strength parameters, which are known from spectroscopic databases. So then this simple formulation T can be used to get the temperature of the gas. Okay, it's basically you measure from, depending upon the transitions that you choose. It could be the rotational temperature. Okay, if you are choosing the rotational transitions, but then you assume an equilibrium. Okay, where the all translational and the other internal energy modes are in equilibrium. The E parameters there are the lower state energies. So that's an indication of what is the quantum energy of that state. So this is an example where we chose two CO lines. So we wanted to measure temperature in the rapid compression machine. And the reason we wanted to measure the temperature was that there were concerns on how uniform the temperature is in the rapid compression machine, and how does the temperature change when a two-stage ignition process happens. So we chose two spectroscopic transitions here, and you see this a P23 transition and an R14. These numbers P23 and R14, these means different branches of the spectra. P branch and R branch, and then the 23 and 14 means the lower state rotational quantum number. Okay. So we use these two transitions. Again, we make sure that their sensitivity is high to temperature. So on the right-hand side, we are looking at the sensitivity, dr by r to dt by dt, as a function of temperature. Okay, so that number, we would like that number to be higher than 1. What means is that the more change in, smaller change in temperature would cause a bigger change in the ratio that you are trying to measure. Okay. So these are some sample data. So in this case, we use a pulse quantum cascade laser. And so that's why you see the pulse here, the first pulse and the second pulse coming from two different lasers. And then the red is the incident radiation, I0, but then when it passes through a sample which has carbon monoxide, you see the black trace, which is now showing an absorption transition. Okay? So now, just as I said before, by taking the ratio of I0 and IT, you can get the area of this transition, or just the the peak absorbance ratio, and then that can be used to calculate temperature from the formula that I showed a slide earlier. So on the right-hand side, then we are plotting temperature as a function of time in the rapid compression machine. So you have the compression phase, EOC is the end of compression, then you have the temperature remains constant in the black, which is the measured temperature. Then you have the first stage ignition, okay? So this is now a two-stage ignition process which happens in the NTC region, and sometimes to lower temperatures as well. And then the temperature remains constant, increases a little bit, and then the second stage ignition happens, and then it really jumps, okay? So what we are comparing here is the green line is with a simulation, and that, without going into too much detail of this kind of measurements, the temperature measurements help us understand these two-stage processes in rapid compression machine and how we can accurately model, for example, the rapid compression machine. Is an adiabatic core or a zero-dimensional model adequate, or maybe we need to use more multi-zone kind of models to get the information that we need from a rapid compression machine. Like in this case, we see that the model predicts much higher first-stage temperature rise and delayed as well than we measured with the laser. So very useful technique for measuring temperature, this two-stage thermometry, and not only it can be used in shock tubes rapid compression machine, but in a number of other systems it has been applied. Cavity enhanced. So why do we want to do that? So if I want to measure, I showed an example before where we were measuring ppm level of CO2, okay? But if I want to get to even smaller quantities that I want to measure, or maybe I have a system where my path length is really short, and so the absorption or the signal that I get depends proportionally to the quantities that have been written there, the line strength, length shape function, mole fraction, and L. So if my mole fraction is really small, I want to get maybe parts per billion level, then the only option that I have in this technique is to increase the path length. But if that's also limited by my device, then what I do is that what we call cavity enhancement. So rather than having two windows, we put two highly reflective mirrors. So once the light couples into this cavity, meaning enters this cavity, it's kind of trapped in there, okay? So only a small part of light can leave from either one side or the other side. Otherwise, it just keeps bouncing back and forth many times, okay? So what does that do? That effectively increases the path length L, okay? So as I've shown here down here, if you use a mirror of reflectivity 99.9%, the effective path length becomes around almost 700 centimeters. And if you have 99.99%, it becomes 2,400 centimeters, okay? So you can get a lot more interaction of the laser light with the molecules, and that eventually increases your signal, basically, and lets you measure much smaller quantities. Okay, so the one parameter which is important here is shown in this equation here, G, which is the gain, okay? So the gain depends strongly on the reflectivity. So in simple sense, it can be written as 1 over 1 minus R, and that's how we calculate how much gain or how much enhancement you get with this kind of technique, okay? So what's very important here is the coupling. So this is a busy slide, but and maybe a bit too much detail for this audience, but the point here is that what I want to measure is that blue line. So that blue line is an absorption transition, okay? Now within the cavity has some of its inherent modes, okay? So this is where, in a sense, where the cavity will transmit the light, okay? The red is shown the laser. So right now we see in the picture on the left is that there is not much overlap between the red and the cavity modes, the gray modes. And what will that do? It is that will, on the right-hand side, give you a much more discrete kind of a measurement, okay, which is not good. You would want to get a measurement similar to this blue line, which is just shown there as a simulation. So to increase this overlap or coupling between the laser and the cavity, you can do different kind of tricks. So one of the tricks is that, what I'll talk about on the next slide, is called off-axis alignment. So that can decrease the FSR, free spectral range, meaning it can bring in more modes into the cavity, so you can have more coupling. Another trick that we use also is that we scan the laser rapidly. So that means the red line moves across very rapidly, and so then you have more chance of this overlap. This overlap, in simple sense, you can think of as this constructive interference, okay? So you want that constructive interference to happen for you to get a good signal on the other hand, okay? So in an on-axis alignment, so you will have a laser light coming in and then just passing through your cavity on the axis. But in the off-axis alignment, you make it enter at an angle, so it makes multiple paths, those multiple red lines in the cavity, and then exits also as multiple paths. And so it kind of shows that kind of elliptical structure. We can change the shape of that structure as well. But eventually what it does is that it increases however number of extra paths that you get over there. It decreases your effective FSR and then increases the possibility of this coupling between the laser light and the cavity mode. Okay, so it's shown very nicely here in this picture. So if I do an on-axis alignment, you get this kind of orange signal, very noisy. Okay, it's very, very noisy. Then you go to more of an off-axis alignment, so you get that green signal. Okay, so now the noise is reduced, and you can see the absorption line there in the black box. Now, if you go to more of a spread off-axis alignment, as shown in the top circle, then you get this blue spectrum. Okay, so that blue spectrum is much more cleaner and gives you much better signal, and at the same time gives you much more enhancement in measuring the trace quantities of gases. Okay. So we had recently applied this off-axis alignment in the rapid compression machine in order to measure carbon monoxide mole fractions at very low temperatures. So again, you see I have my laser at 4.89 micrometer. It passes through some optics. Then we do the off-axis alignment. We have 2 cavity mirrors installed into the combustion chamber. So I showed you the picture of the combustion chamber before. It undergoes that cavity enhancement there. Then we detect it on a photodetector and then the oscilloscope. Okay, so these are some sample data that we get. So we are able to measure CO shown in the black trace and comparing it with a couple of models just to see how they are able to predict. In this case, we are using very highly dilute conditions, so we are only seeing the first stage ignition. But what really kind of it highlights here is that at these really small quantities, also this cavity enhancement can help us measure the CO mole fraction, and in some cases, like at 870 Kelvin and 899 Kelvin, the models are really off, right? So the models are not even starting to produce CO, whereas we are starting to see appreciable amounts. Okay. So the key message here is that these techniques like cavity enhancement and so forth help us make really accurate and sensitive measurements of species in various kinetics experiments, which again helps us build more accurate chemistry models. Okay, so with that, I can take now more questions on this laser diagnostic part. There will be some question from here in the quiz. Yep.
How does the energy of the laser affect the accuracy of the measurement?
Yeah, okay, good question. So for these absorption-based experiments that I have shown, we use very low power lasers. Okay, so we use lasers which have power of the order of milliwatts. Okay, and the reason is that it's actually not important. You don't want to have actually very high power lasers for these kind of experiments. Okay, why do I say that? Because what eventually matters is just the ratio, right? The ratio between IT and I naught. What is the incident intensity and what is the transmitted intensity? Okay, so even if you start with a small milliwatts, as long as your photodetector is sensitive enough, okay, to measure that amount, that just works well enough. Okay, because if you go to extremely high power lasers, then the process may not remain non-intrusive, right? So sometimes this is seen in especially some of these pulse burst lasers, right? It's seen in some cases that if you go to these rapid, extremely high power in a very small amount of time, it may actually cause, for example, some dissociation of molecules, right? So you have to choose that appropriately. Having said that, in some other techniques, like in laser-induced fluorescence, you cannot work laser-induced fluorescence with low-power lasers because your signal there is directly proportional to the laser power. So you have to use relatively high-power lasers, but still you want to make sure it's not high enough that it will cause some intrusiveness to the system that you're studying. Yep.
Yeah.
Can we use microflow reactor to understand the ignition delay phenomena, especially at low temperatures?
Microflow reactors.
Yeah.
Did you say microflow? Yeah. We have experts here on microflow reactors. I did not talk about the microflow reactor. The microflow reactors can be, what I've seen is can be used actually to even look at cool flames, right? And low temperature ignition. And I think it's a very, very valuable device. And then in some cases could also be linked to the octane numbers of the fuel, right? Because that's where the cool flame or NTC region is, you get the most sensitivity to octane numbers. So the short answer is that I didn't talk about that today, but it's also a very valuable device, the microflow reactor.
Okay.
Here, on your back.
In the cavity-enhanced diagnostics, you have two mirrors, right?
Yep.
The picture that you showed in the left mirror, the laser signal goes from like all over. How does it pass in the off-axis?
Okay.
Yeah, this picture.
This picture? So
yeah,
in this case, the laser is entering from the right. Okay, so the laser is the 4.89 QCL, that's the laser, right? So it goes and it enters from there. So what is your question? Repeat your question again.
So it's an off-axis, right? And cavity-enhanced. So we have two mirrors.
Yeah, the blue are the mirrors.
Yeah, so the left mirror, how does the laser signal pass like from all over, like from top to bottom?
Okay, so first of all, because it's a highly reflective mirror, I think in this case we were using maybe 99.5% reflectivity mirror, okay? So the total light that you have, right, the sum should be equal to transmission plus absorption plus reflection, right? So most of it, 99.5% is going to get reflected, right? So only a small amount minus the absorption will get transmitted through the mirror, and then it enters the cavity, okay? That's the first point, okay? Now, once that light enters the cavity, the off-axis alignment means that it's just a little bit off, right? It's not going exactly parallel to that. Now, it enters that, and then it goes and hits the second mirror, okay, traveling at an angle. We've shown kind of straight lines there because that's just a cartoon there, okay? And then most of it, 99.5% of that intensity will be reflected back, right? Because that's the reflectivity of the mirror. And then it hits the first mirror there, okay? And then only small amount will leak out, and then most of it will go back forth will go as well. Maybe a more clearer picture is this one, right? So this shows you there over there. If you look at that pattern of the spots that we have, right? That's kind of the pattern that you get on the mirror, okay? So that off-axis alignment kind of sweeps it through, right? In that elliptical fashion, okay? And then after a while, like after you have gone through one full ellipse, right, it will make another sweep on it through, okay? And how many total passes you will get, as I said earlier, that just depends on the reflectivity of the mirror or the gain factor that you will get, okay? Whether that pattern is elliptical or not, in the picture on the left, I'm showing more of a circular pattern that you can actually maneuver around during the alignment process. But what you really want to get is as many non-overlapping passes as possible, because then the physics shows us that decreases your FSR and gives you more interference, a possibility of more constructive interference to get this clean signal, the blue signal that we are showing there. Is that clear? Was that the question?
Yeah, okay. Thank you.
Could you put your shark tube back on?
Which one?
Close by. No, it had shark tube with many, with a laser going through it.
Okay.
And the multipass, was
that
it?
This one?
Right.
This is a cross-section of the shark.
No, the multipass, that was better. It had zinc selenide optics, it had... You just had it.
Or was it the RCM?
There it is.
Oh, this is the RCM, rapid compression machine.
Okay. Oh, I didn't realize it. I just wanted to impress upon everybody that on any given day, when you're trying to do these experiments, you're expecting everything on this picture to work. The oscilloscope has to be working. The black wires have to be good. Yeah. The IR detector, the thumbprint on zinc selenide lens better not be there. In other words, you don't want anyone to touch it, right? And you don't want anyone to touch the calcium fluoride lens, and you wanted a paper bag over the plane mirror so that it got no dust overnight, and you take the paper bag off. And you gotta have to remember to take the paper bag off, okay? And then everything else, and then it's a rapid compression machine. Now, look, I live here and I've done experiments. The rapid compression machine itself hemorrhaged oil one day, just shot oil everywhere. Yeah. It was a bad day. So my point being, every time you add a diagnostic and add another toy to your apparatus, the probability that you actually get to the end goes as the product of all the probabilities that everything works. So it's the probability times the probability times the probability times the probability, and you'll be astonished how hard it is to get everybody dancing together. Any given day you come in, everybody's ready to go except one part. So that's the agony of research. And it's very exciting when it all comes together and you finally do get the data that you put up. And we always smile and we say, typical data. But of course, typical data means the only data I got in 1 month, okay?
I can say the same thing about computation.
Say it, yes.
Yeah, same thing can be said of the computation, especially today's HPC. I mean, every time we have to deal with these supercomputers, they change their operating system, and suddenly the perfectly finely working code stops working. It doesn't compile, and so on. So the chances of getting 50 million hours of simulation in a single shot is nearly zero.
Well, I might add, it should bother you, I'll get you, it should bother you that we did change the operating system on our computer way back in 1985, and then we ran our turbulent code and we get a different answer. And imagine that you're balancing your checkbook on an Excel spreadsheet, and then you buy a new laptop computer and your bank account changes. Question over here.
Okay. Thank you for your presentation anyway. I have a question about the jet stir flow reactor. So if you consider the temperature inside the reactor and another temperature at the output line, so in this way you have a temperature gradient between the in and out, or if you consider one temperature.
I think you want to maintain a uniform temperature, and you want the change to be, because of any exothermicity in the system, to be very small, right? Mm-hmm. But her question is, what temperature do we actually report? Is it the inlet, outlet, or the middle temperature from GSR? So she's saying, is it how uniform it is throughout the length?
Okay.
Within 5K. So that's
okay, you consider one temperature, just along the flow.
So that's where the reactions are happening, right? So
okay.
Maybe the picture is way too back, right? But yeah, this is the core of the reactor, right? Okay. Where all the reactions will happen, as Manny is saying, is within 5 Kelvin is the entire temperature.
Okay, so you do not consider the oscillation, for example, that happens in a jet stir flow reactor. I mean, this is my question. So if you consider the oscillation between inside and output of the reactor.
Oscillations, you mean flow oscillations or temperature oscillations?
Oscillation of temperature, just output of the flow inside of the reactor, and then in the output line. I think that there is a different temperature, I mean.
Yeah. Okay. So what Manny is saying is that some people operate the GSR to do extinction ignition experiments,
mm-hmm, yeah.
right? And in that case, maybe that's what you are referring to. That's what happens. But kind of what I showed and what is usually done here in Manny's lab is
it's very small, maybe the reactor, so it's possible to not consider the oscillation?
The temperature remains uniform in this case.
Yeah,
You're using
okay.
highly dilute, and so there's not much exothermicity there.
Okay, thank you.
Yeah.
Hey, so I have a question about, what about solid fuels like biomass, which is more complex fuel? And for example, in the field of pyrolysis, which of these methods or which method do you think is the best to obtain kinetic parameters? And also if you think in the future would be possible to predict wildfires, for example, through kinetics?
Okay. Both are good questions. The solid fuel, first of all, we don't do much work here, at least in our center, on solid fuels. Okay? What you can do is that you need basically different kind of reactors, right, to study biomass. And one of the key things there is the pyrolysis process. Okay? So you can use some kind of a pyrolysis reactor, okay, and to look at the pyrolysis products coming out of that. Okay? And so there's a very nice group in Ghent in Belgium, right? So they do a lot of work on a lot of experiments as well as modeling of the biomass process. Okay? I would say in terms of the techniques that I have shown, these are mostly designed and done for liquid fuels or gaseous fuels, right? Solid fuel, whether it's biomass or coal, you basically have to, it becomes very complicated also, I should say. The biomass, right, it's just its nature can change a lot. Can you really put together a detailed chemical kinetic mechanism to describe the pyrolysis or oxidation of a biomass? Probably not feasible, right? So you use a lot of lumping kind of techniques, as is done in Italy, in Milano, okay? And then you try to have a simpler representation of that, okay? So it's more complicated, the biomass pyrolysis and oxidation. What was your other question?
Yeah, if you think it will be possible in the future to predict wildfires or like environmental or social application of kinetics in the field of combustion and pyrolysis.
So one of the things which our models at least can even do right now is that we can predict the emissions, right? So we can predict how much emissions are going to come out from the exhaust of a car, from a power plant, and so forth, right? And on top of that, Manny's group has a project now where they're also looking at how these emissions interact with the aerosols in the environment, right? Mm-hmm. And how the atmospheric chemistry is affected by the emissions coming out of, for example, power plants and so forth, right? So yes, the same kind of chemical kinetic techniques that we talk about for ignition are many times applicable to atmospheric chemistry as well. I was talking about this low temperature oxidation of RO2 going to QOH and chain branching pathway. These kind of highly oxidized species are also very relevant for atmospheric chemistry, right? And actually many times we are learning from them on what they have learned on a specific reaction in the atmospheric chemistry world, and then try to apply that or extend that to high temperatures in the work that we do. And sometimes it happens vice versa. But specifically, so the simple answer is that yes, the techniques can be used for atmospheric applications as well. To predict wildfires, your specific question, I'm not sure if anyone can predict. I don't know if you have a good answer to that. Can we predict wildfires?
Wildfire?
Wildfires.
Like a forest fire?
Like forest fire.
Yes, of course, people try very hard to predict that. Those are the true pioneers of combustion. So you ask a question, sort of, how do we know the pyrolysis of wood? Mm-hmm. That's also pioneering. By comparison, the gas phase, single molecules, that's sort of the pure and pristine stuff. The hard work is getting down into, very strange things. We rely upon the understanding that we gain from these basic concepts to help us try to understand something like a wildfire. Now, we saw lectures on premixed flame propagation a couple of days ago, and your first reaction, mine would be that wildfires propagate much like a premixed flame. Well, actually, they sort of don't, okay? when you're burning down a tree, there's lots of ambers and things that lift up into the air, and the wind blows them forward, and they fall into the fresh forest and set the forest on fire. So it's a whole different propagation technique. It's way different than having a preheat zone and having radicals flow forward into the unburnt gas. Here we have what we call a firebrand, just hot burning embers that get pitched into the air and then fall into fresh burning stuff. So, and people, of course, there's lots and lots and lots of money bet on when you see a fire, can you predict in 3 hours where it's going to be and whose house will burn down and whose house will not burn down, and where should you send the fire department? This is really a burning issue.
Thanks, Bob.
Thanks. Okay, thank you very much for your presentation. You didn't talk about mass spectroscopy, but I would like to know your opinion about this technique in comparison with the others.
Yep.
And also, I have another question about waste-derived fuels, for example, biodiesel, or I'm not talking about solid fuels because he already asked you, but what are the difficulties in characterizing these fuels and to make these fuels like standardized to use it?
Okay. So the first question, mass spectrometry. I talked about it a little bit, but not in detail. So I talked it maybe more in the context of when you do DHA, then you have a GCMS mass spectrometry. I also talked about it that when you have a JSR, for example, the jet stirred reactor, then you can analyze the species coming out of it using a mass spectrometric-based technique, right? So it's a very valuable technique because it can give you a lot of information, right? So you can measure a lot of species. You can basically resolve them by their masses, right? The drawback compared to the laser techniques that I talked about is the intrusiveness, right? So you still have to, for example, these really nice experiments that are done in low pressure flames at the advanced light source, right? So they stick a probe into the flame, okay? A quartz probe, and from there you sample out, okay? You sample the flame products, and then you send it to the synchrotron vacuum ultraviolet light in conjunction with a mass spectrometer. But then the question is that this probe that you put in the flame, what was the impact of this on what you are sampling, right? And there are a number of papers written on that which show that the probe actually affects the aerodynamics around the flame, and the probe affects the temperature around it, right? So in summary, what I'm trying to say is that mass spectrometry is highly useful, but it can be sometimes, depending upon the experiment, intrusive, right? So it's not an in situ technique like a laser diagnostic could be, okay? So that's the advantage of laser-based techniques, is that they, unless you go to, as your question, an extremely high powers, right? Then unless that's the condition, the laser diagnostic techniques are very in situ or non-intrusive. But again, mass spectrometry, we also use it in my lab. We couple a mass spectrometer to the end of the shock tube, and we continuously sample through a nozzle to get a list of species which are formed. And once we understand what those species are, then we sort of use a laser to look at one specific species, and that gives us much more pure or much more cleaner information on the reaction kinetics.
Okay, it's because in my laboratory we also use this technique, but many components have the same mass, so sometimes we get in trouble to separate them.
Of course. So that depends on the mass resolution of the spectrometer that you have, right? And that's why what I was saying is that in the lab-based setups, that could be a problem, right? But if you go to these kind of synchrotron-based experiments, then by scanning the photon energy, right, by using this ultraviolet source, then you can actually resolve even the isomers, right, quite accurately. Yeah. So that can be done with some, and there are some other advanced techniques as well, based on mass spectrometry, but how do you separate out different isomers? And then your other question was on biodiesel or biofuels in general?
Yeah, like waste-derived fuels, and if you find it more difficult to do the characterization, or also to try to standardize the fuel to be like commercial.
Yeah, so on the first part, for example, we specifically talk about biodiesel. Biodiesel tends to have a very long chain fatty acid methyl esters, right? They could be as long as C18, C19, okay? So, and then they can have sometimes saturation or not. So their characterization could be complicated because they have very long chain molecules in there. Okay? So that could complicate. But again, a technique like NMR could be used there to characterize them. On the other hand, they don't tend to have too many molecules in there, like as you get in distillate fuel. In distillate, you can have hundreds or so forth components, right? So there's some pre-screening happens, and you have a few molecules. In terms of standardization, I think that's. I know some people are working on that, but that's challenging because it depends a lot on your feedstock, right? Yeah. So what is the feedstock that you're starting with? If it changes one day from some waste wood that you had to another day some other kind of plant, or changes to algae or so forth, then that just makes it complicated. So I think standardization is, people are trying, but it's difficult.
Okay, thank you very much.
Okay, so I think it's good. I actually started off. First of all, thank you for asking these many questions. You guys stayed true to what I said in the beginning, and it was more like a discussion. And I stayed true to my word in diverting the questions also. So I asked people around the room to answer some questions. But I started off with 2 days ago with 200 slides, but I cut those down to maybe what I presented today was 90 or 100, because again, I wanted to have more of a discussion than really showing a lot of material. So thank you for the interaction. What is remaining is the second quiz. Okay, so we're going to have you will enjoy the second quiz. It'll be a little bit harder, and then we are basically done. Okay, so my TAs can pass on the second quiz, and I'm available here if you have any further questions.